And with that, I think we'll go ahead and get started. So thank you everyone for joining us, and welcome to day 3, our final day for the Summit on Drone Geophysics, hopefully the first of its kind. I wanted to remind everyone that we are planning on an additional Summit on Drone Geophysics for next year. So for those who have enjoyed this and would like to help us make another one possible, please reach out to us via ns@seg.org, because we would love to have you on the panel. We're hoping to have a larger, I guess, community participation in the arrangement for next year. If you have questions or anything like that, you can also reach us at that email. So like I said, fall 2021 will be the next one. And then the hope is that we'll move to a geoscience conference as opposed to just a geophysics conference the year after that. So we hope many of you will join us. Then I wanted to thank everyone again for participating. It's been wonderful to have you all. It's been 2 days so far of lively discussions and wonderful presentations. I don't think I've quite enjoyed a conference so much because of the actual interaction between everyone. That's been wonderful. We also wanted to thank all of our presenters, especially those who are in inconvenient time zones for the time slots that we picked. One of the questions that we will be asking in our follow-up survey will be related to time zones for future events, because we would like to make them more friendly on a global scale. So please keep that in mind for feedback for us. We'd also like to thank our sponsors again, and then the SEG Near Surface Group. The Near Surface Group has been extremely active in SEG in the last couple of years and is growing dramatically. So if you'd like to get involved with that, you can reach us through the same email that we keep talking about. And then our sponsors, as always, Geometrics, Pegasus Airborne Systems, Hammer Missions, Drone Automation from A to Z, Sequent, and Southern Geoscience Consultants. We all thank you very much for your contribution to helping make this happen this year. Sorry, lost my head a little bit. Just a quick reminder, if you have questions, I think by now you all know that we'd like to see those in the Q&A box. Once we move to the panelists or the discussion portion, I guess we'll do those out loud as much as possible. So we'll review how to do that when we get there. If you have any problems, please send a message to the panelists box, and if possible, Lori or I as the head for that. When you ask your questions, please include the name of the presenter you are addressing, so that way we can make sure your questions answered by the correct person. If you have general questions, you can also put those in the Q&A box. And then last but not least, we are recording this as we have the other 2 days. So the recording will be available in the weeks following this. It's not going to be available immediately, but all of you will have access to that as a part of your registration fee you've already paid. So if you need to review anything, you'll have access to that link soon, hopefully. And then unless Ron would like to add anything else, we'll jump straight in.
No, I think you did an excellent job of doing the proper announcements and welcoming everybody. I wish to on my own, I wish to welcome everybody. This has been a wonderful workshop. It succeeded far more than what we ever expected it to be. And I hope that you will get fired up about drones and using them for geophysics, and I'll stop talking at this point. All
right, without further ado, I'll introduce our first speaker. Our first speaker of the day is Steven Vanderbeek with Medusa Radiometrics, and he will be talking to us about gamma ray spectrometer for drones. Steven, are you ready?
Yes, I'm ready.
Wonderful.
Do you see my screen?
Yes.
Great. Okay, so great that I can start off the first of the last day. For me, it's time to get some drink, but for you, it's still in the morning. As introduced, my name is Steven van der Veek, and I'm an R&D engineer at Medusa Radiometrics. This is a company in the Netherlands that builds gamma ray spectrometers, mainly for geophysical applications, but we also do a lot of specials. And lately, we've been using these spectrometers on drones. I combine this position as an R&D engineer with a PhD position at the University of Groningen. The topic of my PhD research is using gamma ray spectrometers on drones. So basically in this presentation, I'm going to share what I've been doing for the last couple of years. This presentation consists of 3 parts. In the first part, I will talk about the technological developments that had to be made for measuring with drones. Next, I will briefly discuss why the current data models should be adapted for drone-based gamma ray measurements. And finally, I will share some case studies of measurements we have done with the drone. So let's start with the main question that I'm going to answer in this presentation. And that is, can drone-based gamma ray measurements accurately predict the radionuclide concentrations in the ground? Besides this, we should first consider why do we want to use drones for gamma ray measurements? Well, since this is a conference about using drones in geophysics, I can assume that you are all convinced that drones have something to offer. But gamma ray measurements are historically used in airborne measurements. And compared to this, drones offer a much better movability. They can fly lower to the ground, and they are more economically affordable. But all these things are also true for ground-based measurements. However, if we take a look at a measurement we have done in the past, we can find an obvious benefit. And this was a measurement done in the Spittelwasser region. This is an area in Germany. And as you can see, it was quite a hell of a job. The goal of the survey was to map the floodplains of a river in search of pollutions. So it was very wet. And this brings us maybe to the biggest advantage of using drones for gamma ray measurements. Drones can enter dangerous, rough and wet areas because they just can fly over it, while the operator remains at a safe distance. And the measurements keep their high spatial resolution, as with ground measurements, because they can fly very low to the ground. And the Spittelwasser project led to the conclusion that these type of gamma measurements can and should be done differently. Now, the first step in using gamma ray spectrometers on drones is a technological step. The conventional systems used in airborne systems are huge and heavy. And this is for a good reason. Volume and mass capture the gamma rays. So a reduction in volume and mass will mean a reduction in your signal. But we thought that this reduction would be possible. Firstly, because drones can fly much lower and slower than aeroplanes. Thus the signal is less attenuated by the air and more signal is captured because of the slow flying. Secondly, we think we can use smart data analysis algorithm to get the most out of your signal. With this in mind, we have developed an initial gamma ray spectrometer that weighs less than 7 kilograms. This was a cesium iodine gamma ray spectrometer, and it contained a 1 liter crystal. And as you can see in the picture, it still had an external GPS. Well, this initial development has led to a whole series of what we call the next generation of gamma ray spectrometers. The series consists of the biggest, a 2 liter scintillation crystal, but also includes a 1 liter, a 700 milliliter, and a 350 milliliter gamma ray spectrometer. All of them are autonomous, as is required for using it on a drone. It now has an integrated GPS, an integrated pressure, temperature, and humidity unit. It stores and analyzes the spectral data in real time. And you can inspect this recorded and processed data during the survey by using a wireless Wi-Fi connection, or it can be beamed down through the remote of the drone. With this new generation of light and smart detectors, we started to do drone-borne gamma ray surveys. With this next generation of autonomous spectrometers, we imagined that gamma ray surveys would start to look something like this. Kick back, have a beer, and wait until the drone finishes the survey. But of course, this is not the case with new technology. We have lost a couple of drones and we have faced some difficulties with obstacles. This is because we want to fly as low as possible, and there you have to deal with all kind of objects like trees and bushes and stuff like that. But this is mainly an issue of survey planning and obstacle avoidance of the drones. And we faced some difficulties in the past, but the newer drones are much better in avoiding these obstacles and have these sensors that keep away from the trees. So it is harder and harder to crash one, and we think this will only get better with time. Fun fact though, none of the detectors have been lost due to the crashing of a drone. And that's because we use cesium iodine as the scintillation crystal, which is very robust, and the shock absorbing housing also keeps away from the damage. So before we move to the case studies, we have to talk a bit about the corrections that are needed to be applied to the airborne gamma ray measurements. The measurement height is important because the gamma rays experience attenuation by the air through which they travel. And at the same time, the footprint, which is the amount of soil emitting radiation that ends up in the detector, increases with height. Corrections for attenuation have been developed for conventional airborne measurements. However, the manifestation of both these aforementioned processes is significantly different in the operating range of a drone, which is between 0 and 40 meters elevation. I do not have the time to go into too much detail during this presentation, but quite recently we have submitted a paper which describes how this process works. And the conclusion of this is that if we use a theoretical model and Monte Carlo simulations, we can quite accurately predict the response of these gamma ray measurements. And therefore, we can correctly analyze our spectra recorded with the drone. Now to the choice of drone, we have experience with several drone types, as you can see. We did some measurements with the small helicopter version, which has great airtime, but less stability. Also, we have done measurements with a huge gas-powered drone that could handle payloads of more than 100 kilograms. The unit could even lift the conventional airborne system of 70 kilos. But for most of our measurements we have done, we used an off-the-shelf heavy-duty DJI M600. And our conclusion is that this M600 is a very good trade-off between airtime and cost. So instead, if you're building a drone specifically for your application, that's always best. But if you have the opportunity, if you don't have the funds for this DJI M600 is a very good option. And we've reached air times of up to 25 minutes on a single battery set. So now to the case studies. The first case study we have done with our new generation of spectrometers was a validation study. We measured an agricultural field from the ground with a 2-liter scintillation detector, and from the air with a drone with a 1-liter scintillation detector. The field was approximately 500 by 500 meters, and it was used for agricultural purposes. Both measurements were validated with ground samples analyzed in the laboratory, and this shown that with statistical accuracy that both detectors in fact measured the same thing. And if you look at the picture, you can see that similar structures are present in both figures. Low concentrations are on the left and on the top, and higher spots to the right. However, what's also observed from comparing both pictures is that there are more small-scale structures present in the left, the ground measurement picture. There seems to be a loss in spatial resolution. And this has to do with the fact that the survey was done at a flying height of 14 meters, and thus the footprint where the radiation originates It's much larger compared to the ground measurements. As a second case study, we did measurements at a legacy uranium mine. This was an area in which each couple of years there has to be done a gamma ray survey to show that the area was not changing. What you see here in the lower part is a water basin. And you can see that the bottom one is filled with water and the top one, even at the time of measurement, was only partially filled with water. And what was surprising about this survey is that we identified a hotspot in the uranium concentrations, something that was not found by the ground surveys. And the reason that this hotspot did not show up on the ground measurements is because the hotspot was located at the edge of the water basin. Since the ground-borne survey was done with the spectrometer mounted on a car, it was not found during these ground-borne surveys. And additionally, it was also not found with an airborne survey that was done of the area by using a helicopter. And this is most probably because the signal emitted by this hotspot was too diluted at the airborne measurement of this helicopter, which flew at 80 meters. And this survey is a very good example that drone-borne gamma ray surveys can really add something to the current existing techniques. It can measure in areas that the current techniques cannot. And this brings us to my final showcase. The Spittle was a floodplain mapping project that I've showed in one of the first slides. This project had kickstarted development of these drone-based gamma ray spectrometers. And as Jens put it, we have redone this survey in 2019, and this time with a drone. The area in the movie actually looks quite nice, and you could easily access this area with a quad. But there were also some very wet areas and areas where there was vegetation that you otherwise could not have mapped. And as a side note, which should be mentioned, during the initial survey in 2016, the quad bike got stuck in the mud countless of times. When we redid the survey in 2019, the drone only got stuck once in a tree. So I think it's safe to say that we are improving. And this brings me to my final slide. The main question I tried to answer in this presentation was if the drone-based gamma ray measurements could actually predict the radionuclide concentrations in the ground. And the answer is yes. And this may be somewhat surprising to everybody who has worked with the huge conventional airborne systems. But the reason why we can use much smaller detectors is because we fly much lower and much slower. And slower means that we collect more signal. If this is combined with the smart data processing algorithms, we can reliably extract accurate radionuclide concentrations. So to conclude, we currently have the technology available for drone-based gamma ray measurements, and we can apply them for agricultural, environmental, hotspot finding, and mine prospecting or remediation study applications. However, an important point has to be made. With our experience in drone-based gamma ray measurements, we have to conclude that this technique is not a replacement for the current airborne and ground-borne measurements. Drone-borne measurements cannot cover the area that airborne measurements can in the same time. And the drone-borne measurements do not have the ease that ground-borne measurements have. Plus, drone-borne measurements are limited by the payload capacity and the flying time of a drone. But drone-based measurements, gamma ray measurements, should be considered as an extension to the current techniques, which with its high resolution and ability to access difficult areas can really add value to a measurement. And I would like to end this presentation with a call to anybody who has an interesting airborne gamma ray study. I've been using this technique and studying the applications for a couple of years now as part of my PhD. And if you have an interesting case, I'm happy to help you by sharing this experience and to help to come up with the survey design. So if you have an interesting gamma ray survey that could be done with a drone, please do not hesitate to contact me. And with this, I would like to thank you for your attention.
Wonderful, thank you. So we have a handful of questions for you, if you are ready.
Great, yeah, I'm ready.
Awesome. So the first question says, I had a very small cylindrical crystal which was blind beyond 1.5 mega electron volts. Is that a problem for the smaller Medusa crystal as well?
I'm not sure if I completely understand this question. Well, you can, oh, okay. I understand. Well, it's a problem if you want to do geophysics with it, because when you do gamma ray measurements, you want to measure the natural occurring radionuclides, so potassium, uranium, thorium. And if you are blind beyond the 1.5 MeV range, you only can detect the potassium and possibly maybe man-made nuclides such as cesium or other pollutions in the area. So I think if you're searching for man-made radionuclides deposited in the environment, then it would be, you can use this, but the Medusa crystals that normally are set to measure up to 3 MeV, thus they contain the potassium, uranium, and thorium windows.
Awesome. Next question. This comment says, excellent presentation. Do you think a swarm approach is reasonable to consider or practical to enhance the signal?
Yes, I think that would be adding something, but again, I think you should also decide what kind of measurements are you doing. If you're doing geophysics and you want to map an area, well, with a swarm, it just goes faster. But if you have the time, it's not a problem. However, if there's a time aspect to it and you want to identify hotspots or radioactive pollution, for instance, after nuclear accidents or something, then a swarm would make sense. But generally, I don't think it's cost effective to implement a swarm if you can do it with a single one as well.
All right. Our next question is, the GRS drone measurement Medusa can be used for mapping different lithologic units at 14-meter altitude, or did we need to reduce the height as it's recommended for magnetic measurements around 3 meters?
Well, it seems that all my questions boil down to depending on what you're looking at. Well, one of the pictures I showed, I can show it again, or I have actually an extra slide for it. And what you see here is the footprint as a result of height. Maybe it's visible, and you see in the top left corner of the moving picture the detector height, and the blue area is the footprint in the ground that's emitting the gamma ray signal. And the exact distances may not be important, but this means that if you fly higher, the footprint where radiation originates becomes bigger. This means that your ability to resolve small spatial structures decreases. So again, if you're looking at very small difference on a short scale, when you are doing hotspot finding, you want to fly as low as possible to the ground. But if you're doing more geological mapping, the differences in signals are mostly not instant, but they are more of a gradient. Then it's okay to have this bigger spot size because, well, the variation is smaller. But this is a very good question, and this is also one of the next topics that I intend to write an article about best practices for using gamma ray measurements on our drone, what it means for what you are measuring. So the flying height and flying speed are part of this.
Wonderful. So you have a couple more questions that are asking about effects like speed and soil types and things like that. And I think I might leave those for you in the question and answer box, because there's a couple others that are a little bit different that I'd like to ask. So one of the questions is, do you consider radon correction in your data processing?
Very good question, because, well, historically, the big airborne measurements do have a radon correction algorithm. And currently, we have post-processing software that can do this. But for this, you have to make some guesses about the influences of radon. So normally, we use full spectrum analysis for the analysis of the radionuclides. And in full spectrum analysis, your radon will manifest itself as in the uranium concentration. So what we do is we normally do the analysis and then try to make an educated guess about the area if the uranium concentration is more or less what you expect. And if it's not, we have some post-processing methods to extract it, but it remains a difficult thing if you only have the measurement at a single height. We have some experience with static measurements in the field, and we see that there is a very strong correlation with radon and rain. So after it has rained, we refrain at least 1 hour before doing measurements just to make sure that this radon is not a problem. And so far what we have seen that this is, in most of the cases, this is sufficient. But yeah, radon is an old problem which is still not perfectly solved.
All right, well, we will move on to our next presenter. He's a familiar face. Mr. Ron Bell will now present. He is with International Geophysical Services and will share his presentation on ultra-low altitude drone EM, a case study in mapping spatial variation and near-surface electrical conductivity.
All right. The title of my presentation is Ultra-Low Altitude Drone EM, a case study in spatial variations and near-surface electrical conductivity. What a mouthful that is. Let me apologize for making it won't seem to go forward. There we go. So what I'm going to talk about today is I'm going to introduce something into the lexicon I hope we all will be using, called dronology. And then I'm going to move to kind of a review of the UAV sensors for mapping geology, and then talk about the GEM2, which is the EM system that I've been working with. And before I get into some of what, in the background, I'll talk about what EM conductivity measurement is. I assume most everybody knows about this, but I feel it's kind of important to go through it again. Then I'll talk about our initial field trial and show a video of that, and then and what we concluded after doing that particular field trial. And then I'll talk about the radar altimeter upgrade I made to our Matrice 600, which certainly is appropriate for other geophysical measurements. And then I'll talk a little bit about our second field trial, which was actually last Friday, a week ago from today. And then I'm going to talk about where we're at, where we're going in our path forward. So geodronology, I've defined it as using drones to map geology and to detect and delineate objects within the subsurface. Basically, we're using physics to image the surface. That's what we tend to call remote sensing, and the subsurface, which was what we tend to call geophysics, to inform us about soil, rock and the buried objects within the earth. This is a diagram, or I guess it's a figure I put together several years ago. I've actually not modified it much. I have modified it a little bit. I'm starting to see some of the things that are filling in the spots. Everything above the blue line is looking at the surface. Everything below the blue line is actually looking at things in the subsurface. And this workshop is if it's anything, it's really demonstrating how far along the geophysics has achieved when using drones, how far we've advanced in the last 4 years. It's pretty remarkable. And so I'm going to visit on the EM stuff. This is most of us know what the basics of the measurement is. You're basically generating an electromagnetic field. We tend to do it at a single frequency when we're working in the frequency domain. It generates a primary, what we call the primary field. Actually, that is the primary field. It generates eddy current flow in the subsurface, which creates a secondary field. We measure both the primary and the secondary field in a receiver coil that's oriented a known distance and orientation with respect to the transmitter coil. And then these data are then converted to conductivity of the subsurface. In addition, the GEM2 will also provide a measure of the magnetic susceptibility, although I haven't done that yet. So the GEM2, the photo in the right, let me see if I can get myself out of the way. The photo to the right is the system. This is it was originally designed, I'm going to say back in the 80s, something on that order, to be a walking system, multiple frequencies, from 300 hertz to 96 kilohertz. It's roughly 6 feet long, about 2 meters. Its sampling rate is about 30 hertz. The coils are oriented in the coplanar orientation. It outputs in phase and quadrature in ppm, and then that's converted to conductivity, susceptibility, and then there's a power line amplitude measurement, so it's obviously extracting the power line signal. The data storage is on board. It's a micro SD. The transfer is either you remove the micro SD or you can actually operate the system by a PC that has a program that communicates with the device via Bluetooth. And then you plug in your GPS antenna. It has a GPS in it. That antenna is typically located some distance away from it. The weight of it is about 3.5 kilograms. The dimensions are basically 6 feet by about 1/2 foot by about 1 inch. So, and it's commercially available. It's been operated. A number of folks have been using this over the years. This is an example from their promotional literature. One of the benefits of having multiple frequencies is that you can perform inversions on those data, depth inversions, and that's what this example is showing. This is an example of a landfill that you can see the apparent conductivity at 16 kilohertz on the left, and the corresponding apparent susceptibility on the right. This is again another application example. I don't have any of my own data to show. I haven't really gotten enough data that I feel like I want to show. But I wanted to also introduce the concept of airborne geophysical survey, and this might be actually better termed a drone geophysical survey classification by altitude. I call the very closest to the ground being super low altitude. That's roughly a centimeter to about 1/2 meter. And in ultra low altitude, which is where I'm actually operating this, I do mag surveys in this domain as well. And that would be about 1/2 meter, about 10 meters above the ground surface. And then low altitude, which is 10 meters to 50 meters. And then normal altitude, which would be sort of airborne domain, is conventional pilot on board airborne domain, being 50 meters to 400 meters. And then high altitude, anything above 400 meters. I would like to have a discussion on this. We can, how to actually describe some of these surveys. I'm trying to at least get some of the terms to be common, if we can do that. Anyway, this is the photo on the right is the system that we, it's mounted on a DJI M600. We programmed the mission. I'm going to show you a video here shortly of our first flights. We programmed the mission with a software called Universal Ground Control Station, which is made by a company in Latvia called SPH Engineering, to follow the terrain using the standard GPS, GNSS navigation of the drone. And we have a 1 meter LiDAR DEM of the site that is available for download from the USGS National Map website. We conducted this flight on May 21st. I think that was the date we did it, when the fields were covered with fairly high grass. The GEM 2 was suspended directly below the drone at a distance of about 3 meters. And the reason for that is that's the distance that we were operating our magnetometer, the mag arrow. And that was the suspension system we had. We just used that right away. And then the frequencies we operated at were 450, 15 and 30, 5310, 18, 303.30 hertz, and 63,000 hertz. So that's a standard arrangement. Let me see if this will work here. There we go. This is the drone flying using the standard sort of navigation. You can see that the navigation, the suspension system allows it to kind of move a lot. That's actually one of the first things we recognized as a problem we were going to have to address. And then this is by definition going into the weeds. It's totally an autonomous flight, and you can see that we definitely need to improve our ability to maintain the altitude above the ground surface in a way that avoids going into the weeds or hitting things on the ground. But for the most part, we were pretty pleased that the drone actually performed pretty well. Even if it leaves a lot to be desired, at least we were pretty encouraged that we were able to actually fly it, collect data, even if we were scraping the ground. At least it was working, and conceptually it was working, but it was obvious we needed to improve our tech. So after this, we spent some time researching several approaches to getting our drone to actually fly a little bit more consistently over the ground surface. There you go. It's flying off into the distance there. There we go. So what we did is we reached out to the folks at SPH Engineering and talked to them about their solution, which is called True Terrain Following. And then we made a deal, purchased their kit that we could then upgrade our drone with. And right there, that is the radar altimeter. It's called a Nano Radar NRA 24. It operates at 24 gigahertz. It's got an effective range of 0.1 meters to about 30 meters, 2 centimeter vertical accuracy, and it weighs about 168 kilograms. 68 grams. They also have 2 laser altimeters, which are as options to this, and they tend to operate at a much higher altitude. So this is the second field trial. We programmed UGCS to follow the terrain. using a radar altimeter. And then once we got it installed and got it working, and then the vertical height control, for vertical height control is we use the radar altimeter, which you might be able to see it. It's right there, I think. And then use the standard GPS of the drone for the lateral positioning. We flew this last week. You can see the fields are dormant, they're brown stage. We suspended the drone about 1.5 meters below suspended the GEM-2 1.5 meters below the drone. And then we operated at conventional frequencies, and then we flew it again about 1 meter above the ground surface. And this is some shots of the drone on task. I'm actually shooting it with another drone that I have. And what you see is, yeah, we do have some movement, but overall, we're probably a bit higher than 1 meter above the ground surface on this one. But overall, we were pretty pleased that it tended to follow it well. You can see it when it does the turn. It tends to get a little pendulum motion, but the drone itself is behaving pretty well. And it also brings up the fact that we have sensor modes, more than likely are going to have noise in our data due to the movement of the sensor, either back and forth, side by side. So that actually brought up another problem that we're actually going to deal with. I know that's pretty boring after a few minutes to watch this, but this actual measurement, I mean, using a drone to actually map or to visualize or take a video of the thing while it's in flight was actually very instructive for us. That's off in the distance there's a canopy. That's where we're actually flying our mission from. On this case, we never actually went out to the field and walked the field. We pretty much set up on the road and then flew from there to where our site was. And that was it. And then we brought it back. Let me go ahead here. All right. The path forward, this is where we're at now. We're going to conduct UAV noise tests on the drone. We've actually done that. What you see there is on the right is a cart that we're using a ground magnetometer that I have access to. And then we would run the drone from startup through full power. And it's actually mounted on that board at the top of the cart. And then we reposition the magnetometer and move it away from the drone, and we run the test again. And the idea there is that it's a quick and dirty way of, well, maybe not so dirty, but it's a quick way of getting a sense of what the magnitude of the noise that is being generated by the drone on either a magnetometer or the EM system. We did the same thing with the EM system. Then we're going to determine what our optimal suspension distance is from that data. How far away we have to mount the system. Some people have mounted these things on the legs of the drone. I didn't quite want to go that route. And then we're going to design and fabricate a rigid suspension system. We got some designs in mind that we'll be testing actually in the next week. Then over time, we'll add an IMU to the drone, to the GEM-2. We'll upgrade the GPS so that we can actually do RTK positioning. That's not an easy thing to do. So far, it's not been evident that we can actually do it with the M600. And then we're going to develop a data plot processing workflow. So at this point, I am at the question stage. Pretty much done with my talk. So.
Wonderful. Well, you left us 2 minutes for questions, which is perfect. We have 2 questions for you. Oh, I lied. We've got more questions for you. We'll start with 2. With respect to roll, pitch, and yaw, were you able to monitor the coplanar vertical dipole configuration? If so, to what effect?
No, we haven't done anything in terms of monitoring the roll, pitch, and yaw as yet. That's part of our learning curve that we're going to be rising and climbing in the next couple of months. So.
Wonderful. Next question. Ron, the use of radar altimeter is exciting. The barometer, oh, sorry. Question came in and moved my question chat. The barometer used in my personal drone is quite susceptible to sudden weather changes. How long until we can see integration with front, side, and back sensors with the radar altimeter to ease worries of intersections of flight lines with topography and other obstacles?
You know, that's really the sense and avoid question, and the answer is that I'd be working on it today if I didn't have the need to first understand and monitor the vertical height. Once I get that done, then we can move to actually adding on the other sense and avoid stuff. So is 6 months we could be starting it. Right now I'm really trying to keep my focus on one problem at a time.
All right. I think, Ron, there's one or two more questions for you in the chat. And then I know that there is one comment that I have moved to the answer section that I think was directed to you. So if you want to take a look at those, I'm going to go ahead and move on to our next presenter. All right, on to our next presenter. A familiar face for those who were with us earlier. Johannes B. Stoll with Mobile Geophysical Technologies will now share with us on his talk, Semi-Airborne Electromagnetics Using a Multicopter. Johannes, are you ready?
Yes, I am.
Wonderful.
Good morning, everybody. I'm still in the wooden house in the middle of nowhere in Norway. We had an excellent operational day today with our drone and finished one area. Yeah. All right. I have 5 topics. First, I would like to talk a little bit about future trends in airborne electromagnetics. Then I would like to introduce the concept of semi-airborne electromagnetics. It show you our multicopter-based semi-airborne EM system, and finally present results from we call it Donnern site, test site in the very northern part of Germany. As we already know, we live in a transition time. We want to, so in the future, we expect that resource exploration for a net zero emission future becomes very necessary. And at the same time, we have to recognize that the future demand, for example, for copper will increase dramatically. It is expected in the next 30 years, 25 years, that, for example, the copper, the demand for copper will double the value we have already explored in the past 150 years. Second, it's already known that exploration has to be done under deeper cover. And this is a very important issue because most airborne electromagnetic systems can look only to a very limited depth. And also there is a difference between the demand in industrialized countries and developing countries. Industrialized countries, it's expected that they will require more high-tech metals rather than base metals. So this also has an impact on the kind of exploration we have to do in the near future. This slide is quite complicated to explain. In essence, it tells us that in the early life of a mining area, the costs are very low as long as geophysics and geochemistry is not involved. So the managers of a mining company wants to avoid the time where they have to spend a lot of money for geophysical exploration. But at some time, when sometimes they have to make a decision where to place the drilling sites. And in most cases, it heavily requires geophysical exploration. I think in this context, UAVs can make a big difference compared to other or traditional exploration methodologies. So to conclude, in the future, it becomes much harder to find so-called tier 1 deposits because, as I already said, we have to look deeper. Especially geophysics will be the one remaining methodology that allows to look deeper into the Earth. And if we don't increase exploration activities in the near future, the industry is already on a critical path to get not enough resources, minerals, to be sustainable. And in the future, geophysical exploration demands for higher resolution, and it must be much more cost and time effective. And we have to look deeper, at least to 1,000 meters. So now I would like to talk a little bit about semi-airborne electromagnetics. Here you see the traditional true airborne systems, which can be subdivided into time domain and frequency domain. I do not want to get too deep into the methodology, but I want to strengthen that depth, the depth of exploration critically depends on the electric power generated on an airborne system. Here you see the different types of systems which are being used by the known airborne exploration companies. And in the table on the right side, you see the maximum depth that can be achieved. And it becomes very clear that if you are able to produce a high moment, you can look several hundred meter deep, down to 1,000 meter. So there's a clear correlation between the moment, the magnetic moment, and the maximum depth. In Germany in 2016, a research and development project was founded by several partners from academia and research institutions using a big helicopter from the Federal Bureau of Natural Resources, which is shown here in the center photo. Semi-airborne means the source is located on the ground and the receiver is flown airborne, is airborne. The advantage of this methodology, which was I think introduced in Japan in one project already in 1998, and then described in a geophysics paper by Richard Smith and others in 2001. The advantage of a ground source is that the moment can be controlled by increasing the spacing, the distance between the electrodes first, and second, if a generator is, if the generator can inject current at very low frequencies, we also can control the depth of penetration. So the depth, but also the depth depends on the frequency band receiver can achieve. So now I would like to speak a little bit about the concept of multicopter-based semi-airborne EM. Our semi-airborne system is performed in the frequency domain. It means we inject an electric pulse into the grounded wire. We generate not only the fundamental frequency, but also generate a lot of harmonics. A lot of harmonics means we generate frequencies, we generate maybe 1,000 harmonical frequencies up to 10,000 hertz, or sometimes up to 100,000 hertz. So in this case, the response we are measuring airborne can be displayed over a wide range of frequencies, which is shown here in this in this graph. And due to the fact that the response is a complex value, it can be divided into the in-phase part and in the out-of-phase part. But we have to take care about the fact that we are traveling with our receiver from near field through the transition field into the far field. In the far field, the electromagnetic field we are measuring is more or less a plane field, but which is a good thing. But if we are close to the transmitter, we are in the near field, and which means the separation between between our receiver and the transmitter is small against the skin depth. And physically speaking, this has the effect that the response we are measuring depends very much on the source geometry. Practically speaking, it requires to measure exactly the position and the course of the cable we are using in the field. Here you see our system. It's a multicopter, an octocopter, which has a maximum takeoff weight of 25 kilogram. It carries a 3-component induction coil system, which is in the blue box. We are also using a high-definition miniaturized acquisition system, which records 3 channels, H, X, Y, and Z. The sample rate can be selected up to 132 kilohertz. And we were able to miniaturize it down to a weight of more or less 6 kilogram. The original system weighted 12 kilogram. We have other sensors, an inertial measuring unit, which allows to also to sense attitude, the motion of the sensor below for further corrections. And we also have a 3-component flux gate sensor, which can be used in future projects to extend the frequency range down to several seconds, maybe 10 or 100 seconds, to allow us to increase the depth of penetration. The multicopter was specifically designed for this semi-airborne system. Here you see a plot that compares the endurance, plots the endurance versus payload. Our system weighs, the complete system weighs about 8 kilograms. And with this payload, our helicopter can fly up to 30 minutes. Here in this plot, you see the signal that was injected into the grounded wire. In the upper panel, you see the time series of the current. In the lower, the spectrum. And in the right figure, in the upper panel, you see the time series of the electromagnetic field of the EHC component measured over a time interval of 4 seconds. And in the lower panel, you see the spectrum. The fundamental wave is clearly detected here. It's about 83 hertz and followed by a lot of harmonics which we can use to estimate the response. The test site, the test flight area was about half a square kilometer, which was flown within 2 flights. We required only 2 flights to cover this area. A and B indicate the positions of the electrodes, and the red lines show the flight lines and cross lines here. Here you see a the typical curves of the electromagnetic field measured along one profile, along this profile. Here you see the horizontal component in the X direction, in Y direction, which is almost 0, and the vertical component has a crossover here at the position of the grounded wire when the receiver flies over the grounded wire. Along a profile, we can estimate the response at certain positions. Here you see 4 sounding curves estimated for at 4 distances: 50, 100, 200, and 300 meters. The real part or the in-phase part, and the imaginary part or the out-of-phase part. The next step is we can use the response and try to model it or invert it, which I have done. I used a numerical model with 1 by 1 by 1 square kilometers, and introduced a layer, a high conductivity layer at about 200 meter depth with a conductivity of 0.05 Siemens, and try to invert the transfer function at a point of 250 meters away from the transmitter. And we found this model here, which nicely fits the measured data. The dotted line is a model for the real and imaginary part, and in the right panel you see the model. This model indicates that in this area there is a very high conductivity layer with resistivity less much less than 1 ohm meter. And I do not want to show you a geological model, but we know that there is a salt dome about 1.5 kilometers north of our test area. And we think this high conductivity zone is generated by brines or salt water in an aquifer at that depth. So my conclusion is, I think semi-airborne could be interesting methodology for future applications, especially in the base metal and critical mineral exploration. Maybe it can be used in the exploration for geothermal energy or carbon capture and storage. And last but not least, in groundwater exploration, which comes more important in the near future due to the climate change. But there are some tasks. We must increase exploration depth. I think semi-airborne can do that. And due to the carbon dioxide problem, we might think about doing carbon sequestration. So this could be also used to monitor as a monitoring tool to monitor this storage. And finally, especially in groundwater exploration, it could be, or in geothermal systems, it could be an interesting tool to monitor artificial fractures. So thank you very much for listening. I'm grateful, Ron and Morgan, to present my results here.
Hello, everyone. We're can you hear me, Morgan?
Yes, I can.
Oh, excellent, excellent. We're back again from our quick break, which frankly, I was watching some of the questions come up, answering a few myself, and found that to be very, very intriguing and interesting. The next speaker is Brendan Ray with Southern Geoscience Consultants. The topic of his presentation is UAV magnetic data, QA, QC, processing and survey planning. Brendan, it's your turn. Welcome.
Hi, everyone. Can you guys hear me?
Yes, we can.
Yes.
All right, I'll start sharing my screen. Let me know if you guys see that come through.
Yes, I can.
Okay. So unfortunately, it's 1:20 in the morning here, so I wasn't sure how acute I was going to be with my presentation, so I decided to pre-record it. I'm just going to play that for you guys and let me know if there's any technical difficulties with that coming through. Otherwise, it's going to be right on 20 minutes, I think.
I actually don't see your screen. Oh, there you go.
How's that?
Perfect.
Might have to turn off my video. Otherwise, you might see two of me. Hi everyone, I'm Brendan Ray from Southern Geoscience Consultants, and I'll be presenting to you about UAV survey planning, QA/QC, and data processing. The purpose of this talk is to provide you with planning and processing considerations for drone magnetic surveys so you can get the most out of your data. The information that I'm going to be sharing with you today is a combination of about 3 years of my experience gained in the industry from personally QA/QCing, processing, planning, and interpreting UAV magnetic data sets. My experience has been in the field of mineral exploration, where I've performed a number of live QA/QC assessments as an independent third party for UAV, fixed wing, and helicopter magnetic surveys. My specialization is in post-acquisition data processing, where I've had a look at over 20 UAV magnetic data sets from a number of contractors all over the world. The processes that I outline in this talk represent the actual steps that I undertake when dealing with a UAV survey, and how I transform the data from being just a contractor-supplied database to a final suite of polished images, which the client can then integrate with other data sets. Examples of bad data that we've come across are ones with significant altitude deviations where the resulting magnetic data has been clearly impacted. We've also seen data that has been poorly processed by the contractor, whereby significant spatial and magnetic artifacts remain visible in the final data. And finally, we've seen a number of data sets which have been delivered as a single continuous line, or where turnaround flights, flights to base, and duplicate lines have been left in, requiring significant amounts of additional time and costs to correct for. It is important to keep in mind that not all drone contractors are going to provide you the same level of data quality. This comes down to the contractor's experience in processing airborne data, but more importantly, the level of noise contained in the raw data. We were fortunate enough to have a direct comparison between two drone contractors with similar line spacing at 20 meters for contractor 1 on the left and 25 meters for contractor 2 on the right. The mean terrain clearance for the two surveys were 45 meters for contractor 1 and 25 meters for contractor 2, respectively. What we expected to see from the first contractor with the higher flying height is a suppression of the higher frequency geological signals. However, this was clearly not the case, as the inherent noise in the system was much higher than that of contractor 2. This resulted in a higher frequency overprint or chatter in the gridded data. Once you start applying higher level filters such as vertical derivatives or AGC filters, the noise in the data becomes increasingly apparent, and even distinct anomalies such as the one highlighted by the red circle become drowned out by noise. The inherent noise of drone systems may be out of your control, but I'm confident that through adequate survey planning, you'll be able to minimize noise through other means and acquire data more like the second drone survey I showed before. So, you want to fly a drone survey? If so, the first thing you need to be considering is the terrain. Will you be flying in flat, hilly, or forested areas? What is the cost benefit of drones versus ground, fixed wing, or helicopter surveys? What data sets do you require? Is it just mag, or do you need elevation or even radiometric data? How should your line spacing, line orientation, and flying height be planned? What is the size of your target? Will the chosen line spacing be adequate? These are just some of the things that need to be considered, and I will expand a little more on some of the key points in the slides that follow. Based on our assessment of the number of drone data sets that we've come across, we feel that drone mag surveys fill a niche that is situated somewhere between conventional air mag surveys and ground mag surveys in terms of the cost, survey size, line length, ground clearance, and data resolution. It has the other surveys beat when it comes to safety, where it takes the cake with the lowest risk of human injury. Drone mag surveys also shine in areas where physical or political access make it difficult for conventional surveys to get the go-ahead. A big drawback with the current state of the art is the lack of radiometric data being acquired as a standard product for drone surveys due to the size, weight, and cost limitations of mounting such a sensor, meaning that if radiometric data is essential for the survey, it is likely that your only option is going to be a conventional air mag system. So, how well does drone mag data compare to air mag and ground mag? Well, I mentioned in the previous slide that the resolution of drone mag data sits somewhere between the other two methods. We have been able to conduct a direct comparison thanks to 3 coincident lines of drone mag, air mag, and ground mag data sets over a strong north-south trending anomaly as seen in the image on the top right. The graph on the left shows us the same set of magnetic data but in profile form, with the ground mag data in blue, drone mag data in green, and the air mag data in purple. We performed an upward continuation filter on the ground mag data to a height of 30 meters to match the elevation at which the drone mag was acquired. This data is displayed in red. What we found was that the upward continued ground mag data matched the drone mag data incredibly well over the entire anomaly. Furthermore, the ability of drone systems to survey at a much lower ground clearance compared to air mag surveys means that the resulting data resolution will be significantly improved in comparison. It is important to keep in mind that the primary factor in defining an anomaly's shape or amplitude is the survey height at which the data is acquired, and not so much to do with the system being utilized, if we assume that all else remains equal. We now know that survey height plays an important role in defining the amplitude and shape of magnetic anomalies along the line. However, to adequately interpolate magnetic features between lines, an appropriate line spacing needs to be used. So what line spacing should you be using? One way of thinking about it is to picture the sampling footprint or ground coverage of a magnetometer as it is taking readings along a line. You can think about this as a cone that expands outward from the bottom of the aircraft. By increasing the aircraft's height, the survey footprint becomes larger at the expense of high frequency information from smaller sources, while decreasing the height does the opposite. If the survey is constructed with a line spacing greater than the flying height, What you might expect to see are artifacts in the gridded data that have a line perpendicular bias due to the gridding algorithm having to interpolate between lines. If the line spacing is instead less than the flying height, what you are going to get is a data set that has been oversampled. In theory, this leads to a cleaner, less noisy data set. However, from our experience, the cost of over-acquiring these lines of data is not proportional to the increase in data resolution. The ideal survey design is to have a line spacing equal to the flying height, as this will give you the most bang for your buck in terms of data quality and geological resolution. A suggestion for when designing your line spacing is to take into consideration the size of your targets. Ideally, you want to be able to define your smallest target with at least 2 flight lines. This is so that your target doesn't appear as a single point anomaly in the gridded data, and also to allow for accurate modeling of the body so that strike, dip, and depth information can be determined. Here we have a visual representation of how the data quality changes across several RTP and RTP2VD images generated from a 50-meter line space and 50-meter mean terrain clearance survey flown in a northeast-southwest direction. The RTP2VD images are filtered products derived from the RTP data and is a standard filter used to enhance shallow anomalies. The wider line space data sets were simulated by removing lines of data prior to gridding. We can clearly see that as the line spacings progressively increase relative to the flying height, from a ratio of 1:1 on the left to 8:1 on the right, the ability to resolve smaller scale features is severely diminished, and the appearance of line perpendicular artifacts in a northwest-southeast direction increased quite drastically. The last thing to think about when planning your survey is your line orientation. There are 2 main schools of thought when it comes to this. One is to fly north-south or east-west lines, and the other is to fly perpendicular to geological strike. It is important to know that there are pros and cons to each of these choices, and that the orientation that you choose to fly is likely going to be specific to each area. There may be other factors, such as any pre-existing data in the area, that you may choose to merge your data with, and if such, matching the existing line orientation may be the better choice. One last thing to note is that as the line spacing becomes smaller, say less than 25 meters, the line orientation also becomes less important, as you are basically fully sampling the magnetic field in your area with little interpolation required between lines. Ultimately, there is no perfect direction to fly, but some directions are going to be better than others if you're willing to accept that there may be trade-offs. The key thing is to maintain a consistent line orientation across the survey and not to try to adjust the orientation of individual blocks, as this will just lead to a messy data set that is difficult to interpret. We'll now move on to the QA/QC segment of this talk. Hopefully the person doing your checks are a little bit more attentive than this guy. And if you haven't picked up on what's wrong with the picture, then maybe QA/QC isn't for you. So how should your data be delivered? Well, let's first go through what you don't want to be receiving. You don't want to be getting a dump of all the survey line data as a single line. You don't want to be receiving any ferry flights from base or turnaround segments at the end of your lines. You don't want any noisy data, nor do you want any overly smooth data. What you want to be receiving is essentially the opposite of what I just mentioned, which is a neat database with unnecessary lines removed. Lastly, you want a data set with timelines flown so that the data can be adequately processed down the line. Based on what we have received, more than 60% of the datasets look like the one on the left, and only 40% look like the nice, neat dataset on the right. So what can you do to help ensure that your dataset is like the one on the right? Well, the biggest thing I can suggest is to include a contractual agreement that defines the expected data quality. This is the standard practice in fixed wing and helicopter surveys, so why should it be any different for UAV surveys? These contractual agreements outline the expected values and tolerances for various survey parameters, and any deviation from these will be at the contractor's expense. The best way to ensure that the data is being delivered as promised is to employ a third party to assess the ongoing survey data on a daily basis, to monitor for any breaks in the contract specifications, and to identify any lines which need to be reflown. Some examples of reflight specifications that you could include in your contract are cross-line deviations, whereby the drone deviates from the planned survey line by more than X% of the nominal line spacing over a distance of more than X meters. Ground clearance deviations, whereby the drone deviates from the planned survey height by more than X meters over a distance of more than X meters. Sampling interval deviations, whereby the drone flies too quickly and exceeds the sampling interval over a distance of more than X meters. Drone system noise deviations, whereby the drone noise envelope is greater than X times the system static noise levels, which are determined from a pre-flight prior to the start of acquisition. Magnetometer noise levels, whereby lines with excessive spikes, dropouts, DC shifts, or missing data exceeding X% are to be reflown, or where the fourth difference noise levels exceed X nanoteslas over more than X meters. Base station magnetometer levels, whereby lines with diurnal variations greater than X nanotesla per minute are to be reflown. Note that these specifications are not exhaustive and there may be many more to add to your contract. We'll now move on to talking about data processing. I think some of you in the audience may have come across this device in your time in the industry, but we have thankfully moved on to more advanced methods to help speed things up a bit. The first step in data processing is to ensure that the spatial data that is being collected is accurate. To do this, the point or line data needs to be plotted in a GIS environment so that it can be properly geolocated. Hopefully the data set you have been delivered has been sorted into individual lines and any unnecessary flight paths have been removed. If not, this needs to be done prior to any assessment. The first thing to look out for are any breaks in line continuity, otherwise known as missing data, where the GPS has failed to record proper coordinate information. The second thing to look out for are any sudden deviations of GPS points from the expected azimuth, which may suggest some form of GPS positioning error has occurred. The third thing to look out for are any areas with unexpected cross-line deviations where the drone may have flown off the planned course by more than the pre-agreed tolerance. The fourth thing to look out for are where duplicate lines or overlapping lines have been acquired. These affected segments need to be removed prior to processing as they can cause significant gridding artifacts. The last thing to look out for are areas where the drone has exceeded nominal flying height by more than the pre-agreed tolerance. The best way to do this is to apply a statistical filter to the database, which will highlight these deviations when viewing them on a line-by-line basis. It is important to note that some of these issues, such as items 1, 3, and 5, cannot be corrected for once the data has been finalized, and as such, need to be rectified during the QA/QC process. If done successfully, you can expect the delivered data to go from looking like the image on the left to the one on the right. Once the data has been corrected for, you can then perform proper assessment of the magnetic data, either in gridded form or as profiles of each line. Alternatively, you can move on to more advanced processing routines such as tie-line leveling or micro-leveling if you are satisfied with the quality of the magnetic data. When assessing the magnetic data in profile form, the first feature to look out for are DC shifts, whereby the magnetometer appears to record data over several points with a momentary change in the baseline amplitude. If these are not extensive, they can just be manually adjusted in the database by adding or subtracting the required value across all the affected points. The second and most common feature that is observed are spikes and dropouts, whereby the magnetometer momentarily records a notable increase or decrease in amplitude. These features are usually caused by sudden or unexpected movement of the magnetometer and may have amplitudes ranging between the sub-nanotesla to tens of thousands of nanotesla. To correct for these features, a linear or spline interpolation function can be employed, but caution must be taken to ensure geological features are not removed. The last thing to look out for are spikes in the fourth difference of the magnetic data, as these can highlight areas where data quality may be poor, even if the noise levels appear to be in the sub-nanotesla range in the unfiltered data. If these spikes are extensive, it is recommended that the affected line segment be reacquired. Another way we can assess the magnetic data is by gridding it up and identifying any regions that display the following artifacts. The first thing to look out for are spurious magnetic highs or lows, which are not spatially extensive. These tend to be caused by spikes in the profile data and should be removed from the data set if they are thought to be cultural or non-geological in nature. The second thing to look out for are any block-to-block leveling artifacts, whereby the difference in amplitude between adjacent blocks can result in a gridding artifact that runs parallel to the overlapping edge between the two blocks. The last artifact to look out for are line parallel busts, which, similar to the block-to-block artifacts, are usually caused by a difference in flying height of a single survey line with respect to the adjacent lines. These artifacts and more can be corrected for using a combination of manual data editing, diurnal corrections, decorrugation, directional cosine filters, or leveling processes. However, these must be applied selectively so that geological information isn't compromised during the processing. When spatial and magnetic data processing are applied successfully, what we can expect to see is a significant reduction in the appearance of noise and artifacts in the data, and on the whole, a cleaner and easier data set to interpret. The figure on the left shows the before and after shot of 20-metre line space TMI data acquired over an existing mine in Australia, where they were looking to identify small-scale structures in the magnetics, as these structures are known to host mineralisation in the area. I haven't included a scale bar, unfortunately, but each image is about 2 kilometres wide. The biggest improvement to the dataset that you can see is the reduction of east-west line parallel artifacts, which disrupt the visual continuity of northeast trending magnetic units. The true extent of the data improvement is only appreciated when a 2VD filter is applied to the data. As mentioned before, VD or vertical derivative filters enhance the appearance of short wavelength features and suppress longer wavelengths, making it easier to interpret lithological boundaries as well as structural breaks. The figure on the right shows the before and after shot over the exact same TMI data, and the improvement is like chalk and cheese. The before shot is completely overwhelmed by noise as well as significant east-west line parallel artifacts. In contrast, the after shot displays a definite improvement in the appearance of geological features, which were difficult to identify in the TMI data. To summarise, drone surveys are still very much in their commercial infancy, and it will take some time and a bit of open collaboration to smooth out any rough edges. As it stands, the quality of drone magnetic surveys that we are seeing now in 2020 as compared to what they were only a few years back has improved quite significantly. Drone mag surveys currently fill a niche that sits somewhere between what air mag and ground mag surveys are capable of in terms of the cost, survey size, data resolution, and more. Drones are very much capable of acquiring good quality magnetic data that is competitive with current standards of both air mag and ground mag surveys. However, this is subject to having proper contract specifications included, appropriate QA/QC being conducted, thoughtful survey planning, experienced post-acquisition data processes, and last but not least, the right contractor for the job. If you lack experience with magnetic surveys, it is recommended that you seek advice from a third party for the following items, as there could be considerations that you have not thought of that may be critical to the success of the survey. Well, that marks the end of my talk. Thank you, everyone. And I'm sure this joke has been made 100 times before, but I'm going to include it anyway. Sorry for droning on.
Wonderful. Thank you. We have one question so far, and that's probably all we have time for at this exact moment. The question is, what is your rule for tie line spacing? What do you think of tie line spacing equal to survey line spacing?
Well, in the mineral industry, what we typically see are tie lines that are spaced about 10 times of what the survey line spacing is. I think sampling tie lines equal to the survey line spacing is probably overkill, because you're essentially collecting the same data twice over quite a few areas.
Wonderful. Well, thank you for your presentation.
Yeah, I actually think some of the questions will probably be transferred into our discussion session as well. So thank you, Brendan. And now for our last presenter, Calum Walter, who is at Queen's University. He's finishing up his PhD. And the title of his presentation is Characterization and Mitigation of Unmanned Aerial Vehicle Electromagnetic Interference for Geophysical Surveying. Take it away, Calum.
Awesome, thank you very much. Yes, so my name's Calum Walter, and as Ron pointed out, my talk will be on the characterization and mitigation of unmanned aerial vehicle electromagnetic interference for geophysical surveying. So kind of what we've seen as a common theme throughout the presentations over the past couple of days is that for a lot of the geophysical sensors we have, including magnetometers, we see that they're suspended well below the platforms that we're flying them on. And this is something called the sensor setback distance. And what I want to try and highlight in this talk, which will be pretty technical in nature, is kind of demystifying what these electromagnetic interference signals are and what the sources of them are, so that we can kind of go forward from just kind of having a vague understanding of what causes these signals and how to deal with them, to really being able to apply different techniques to deal with them correctly. So to go over this throughout the presentation, I have three main kind of talking sections to it. The first one is going to be measuring the setback distance during flight. So this will be with a potassium vapor magnetometer. I'll then look at characterizing the electromagnetic interference signals in the lab setting with a fluxgate magnetometer. And then we'll look at characterizing the electromagnetic interference signals during flight. This is with the Geometrics mag arrow with a very high sampling frequency of 1000 hertz for magnetic surveys. So starting us off here, looking at one of the more critical integration considerations, what we have is determining where the magnetometer setback distance should be. So how I've conducted these is with vertical buzz tests, and what I'll go through now is kind of explaining how this is performed. So typically what I do is remove the surveying magnetometer from the multi-rotor UAV, place it in a magnetically quiet environment, and keep it stationary throughout the entire test. This, of course, is to reduce the noise levels that are experienced by the magnetometer so that only the ambient field is sensed, and then whatever the signals from the multi-rotor UAVs or the drones is sensed as well. So when we have this set up, we take off with our drone and fly well above the surveying magnetometer so that the electromagnetic interference signals are not being sensed by the magnetometer. And then in addition to this, we also want to be able to measure what the distance from the multi-rotor UAV is to the magnetometer. And we do this with a laser altimeter. So when you've reached this kind of point, this is when the vertical buzz test would actually begin. And we slowly fly the UAV down towards the magnetometer so that the magnetometer can sense this electromagnetic interference of the UAV. And this is also, at the same time, we're measuring the distance, so we can go combine these two. So what data from one of these kind of vertical buzz tests would look like is in the top in blue, we have laser altimeter measurements, buzzing down to about 2 meters above the magnetometer, going back up and down, and typically you'd repeat this a lot of times. And then we have the total magnetic field readings here, where the sensitivity and the background noise in these sections are roughly around 10 picotesla. So we get a very accurate sense of when the magnetometer starts to sense the electromagnetic interference signals from the multi-rotor UAV. And this is kind of the first onset for a deviation within the signal. So some examples of measured magnetometer setback distances that I've conducted with. So we have a DJI S900. This is kind of the first system we use, one of the kind of smaller UAVs out there and one of the older ones. This had roughly a 3 meter offset distance compared to one of the BFDs, which has more of a 5 meter offset distance. So the main difference between these two different offset distances, and something that's unique to each UAV as well as each magnetometer, is it's going to be different for each one. So the reason for this is because the DJI S900 is a lighter and smaller drone. It has smaller electromagnetic motors, leading to smaller electromagnetic interference signals, in contrast with the larger and heavier DJI Wind 4. So getting a good understanding of where we can place the sensor when it's outside of the field is good to mitigate these electromagnetic interference signals. But for kind of the research purposes I was interested in, is kind of digging into the signal and seeing what these electromagnetic interference signals are actually caused by, with the hopes that we can start looking at different ways to suspend the sensors potentially inside the field, or look at ways that we can mitigate it through compensation, filtering, and other such methods like this. So when we started looking at this, we quickly realized that the dominant source of electromagnetic interference was going to be from the electromagnetic motors, of course. And these are permanent magnet synchronous motors, a very kind of specialized type of electromagnetic motor that is employed on commercially available multi-rotor UAVs. So the two dominant sources of electromagnetic interference that is generated from these permanent magnet synchronous motors, the first one is from the solenoid armatures. And these are where current from the ESC is passed through the electromagnetic coils, creating an electromagnetic field. And it's the interaction of this first electromagnetic field with the magnetic field of the permanent magnets within the rotor hub that actually causes the rotation of the motor and the blades on it as well. So this is a very good technology to be able to have fastly rotating, very quiet and efficient motors. Not so great if we're trying to run geophysical surveys, particularly magnetometer surveys with them. So kind of what I wanted to look at with this was, what are the different signals that are being produced by these permanent magnet synchronous motors? And to kind of give a brief overview of what these motors are and what they look like, we call the configuration of them based off this specific number here, which is 12N and 14P. So 12N refers to the number of stator coils within the stator, or the stationary part of the motor, where 14P refers to the 14 permanent magnet pairs that are located on the outside rotor hub, which you can see here. Also important when looking at the winding diagram is that we can see that these motors are fed by three-phase AC, so red, blue, and green. So for the test that we conducted, what we wanted to do again was keep everything as stationary as possible to limit any motion noise or noise that wasn't specifically associated with the permanent magnet synchronous motors. So we kept both the platform and magnetometer stationary and just very slowly rotated one of these electromagnetic motors manually to see what sort of magnetic interference signals were associated to them. And this, of course, is the kind of data that we got back from this. So here is where the motor is stationary. Then we start slowly spinning the motor for 5 revolutions, as you can see going through the section here, and all of the multi-frequency electromagnetic interference signals that we can observe within the time domain here over the course of approximately 100 seconds. So 5 rotations of the motor for 100 seconds leaves you with all of these high frequency components within the electromagnetic interference signals. So obviously looking at this in the time domain is a little bit more challenging to tease out kind of what the different frequencies and signals are. So this is where we want to perform a spectral analysis of this signal. Let's look at the frequency components of it. So on the bottom section of the diagram here, what we have is the time domain component plotted again, where the amplitude of our signal versus the time. And then this very colorful plot in the middle is a spectrogram, and it plots both the time as well as the frequency component on the y-axis here. So that if we're applying a constant rotation frequency throughout this test, what we'd expect is that there would be specific frequency bands associated to the different signals that we see. And throughout this manual rotation test, what we were able to see is that there are 3 dominant signals. The first one being a mechanical rotation frequency, this being a signal that is synchronous to the mechanical rotation of the rotor. 7 times higher than this, we were able to determine that there was a permanent magnet signal associated to the rotor's rotation. And then even 5 times higher frequency than this, there's an induced magnetic field signal, which you can see here in the frequency domain plot, and as our highest amplitude signal for this motor configuration. So what I want to do is just kind of explain where these signals are coming from and what is the cause of them. So looking at the isolated component of the mechanical rotation frequency compared to, say, the total magnetic field that we measured, you can see the 5 different rotations of the rotor throughout this, just highlighting this component of the signal. So where this comes from is that if we take a look at our permanent magnet synchronous motor, what we want to do is kind of ignore what's going on with the stator at the moment, because this leads to some of the higher frequency signals. Look at what's going on with the rotor and how both the rotor guard and the permanent magnets can induce a signal that is synchronous to the rotation of the rotor. And what typically ends up happening with these is that you get remnant and permanent and induced components of the magnetic field that all kind of blend together, and one side of the rotor guard will be a little bit more magnetically positive, we'll say, and compared to the other, which will be a little bit more magnetically negative, relatively speaking. And as you rotate this, you get these negative and positive blips, that are synchronous to the rotation of the rotor. So moving on to our second highest frequency signal, this is the signal that's related to the permanent magnets. It's 7 times the mechanical rotation frequency. And looking in the time domain, if we look at one cycle of the permanent magnet, or the rotation of the motor, we can see and count out the 7 different oscillations due to the permanent magnets. So explaining what this signal looks like, again, we're just going to focus on the rotor here. And as we have all of these different permanent magnet pairs, just with different orientations, aligned next to each other, and when we rotate them, we get these negative, positive, negative, positive, negative, positive, negative blips in the data as we rotate them past our magnetometer. So obviously, because there's 14 magnets, they're all oriented in opposite directions. This leads to our 7 times the mechanical rotation frequency as we rotate these rotors. And then finally, the more complex signal with this is the induced magnetic field component. So what I've gone ahead and highlighted in the time domain here is, this is the full kind of test. I've highlighted one cycle of the mechanical rotation and then counted out all of these 35 different induced magnetic field components. And what these result in is the combined effect of the rotor permanent magnets with the stator. And I'll go through now and explain kind of how this works. So looking at just 2 permanent magnet pairs and how these interact with different stator coils, and as well as the ferromagnetic core of the stators, which is more of the important part here. So how these solenoids work is that you have a copper wire wrapped around a ferromagnetic core, or something that's very highly magnetically susceptible. If you pass a current through this wire, you're going to get a magnetic field that's generated. And then because there's a very highly magnetically susceptible material inside of it, you get an induced magnetic field that's generated that amplifies this magnetic field that's created due to the electromagnet effect. So this is great for amplifying the signal due to the input from the battery. However, another consideration is if you have a highly magnetic susceptible material close to a permanent magnet, you'll get an induced component to this every single time that you have the axis of the magnet passing close to this ferromagnetic core. So basically every single time you have one of these magnets passing close to the ferromagnetic core, you get one of these signals that's created. Nice and easy to follow when you are looking at a permanent magnet pair with individual stator armatures. However, it gets really complicated once you start adding 14 and 12 different pairs each. So we can see here, just with rotating the rotor very, very slowly, we get interactions here, 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 here. In fact, if we go and rotate the rotor around an entire time, what we end up seeing is that there's 35 of these different interactions per mechanical rotation that will be picked up by the magnetometer. So throughout the tests that I just showed, this was for a configuration with 12 stator armatures and 14 permanent magnet pairs. And these are the different ratios that we were able to establish based off the mechanical rotation frequency, which is kind of the important thing we need to keep in mind here. So we did this for this specific configuration. However, I also went ahead and looked at a bunch of other different motor configurations, because not all the permanent magnet synchronous motors are the exact same configuration, and plotted out what each of these different ratios were. And this led us to be able to develop these 2 equations, which can predict, based off the mechanical rotation frequency, what each of the permanent magnet frequencies will be, as well as the induced magnetic field frequencies. So this, of course, is just based off knowing what the mechanical rotation frequency is, as well as how many permanent magnets and how many stators are within your system. So also to help develop these, we use finite element analysis within modeling software to be able to kind of back up these 2 equations from the experimental analysis that we did. So plugging everything in, what you can see is that the frequency range for these magnetic interference signals, 50 hertz is typically what a lot of the mechanical rotation of multi-rotor UAVs will be. However, this can vary, sometimes down to 40, sometimes higher than this, up to 80. It just depends on the multi-rotor UAV and is something that needs to kind of be understood prior to surveying. And then you can go ahead, once you know this, as well as what your configuration is, to predict what the different signals are. And as you can see, they go up to tens of kilohertz in some cases. So this is all good when you look at this in the lab and it's at very low mechanical rotation frequencies. It's quite another thing to look at it when you're actually surveying in the field and see how this affects the magnetic interference signals that are being collected. So to do this, what we used was a Geometrics mag arrow with a sampling frequency of 1000 hertz. And what I would like to show is just the difference between if you suspend the magnetometer at, say, roughly what the offset distance is versus if you hard mount the magnetometer right to the UAV, and just some of the different considerations we need to keep in mind when doing this. So looking at a spectral analysis of a flight with a 3-meter suspension length, what we can see in the time domain is that we have one flight line here, around 80 seconds, we have a turnaround, and then another flight line in the opposite direction here. And this is just the raw data that was collected by the magnetometer. The signals we can see is that roughly, again, at 50 hertz, as I said, giving an amplitude of around 1/4 of a nanotesla, what we have is these mechanical rotation components within the signal. And you can see this is pretty constant throughout the survey with a little variation around the corners. One of the other signals we have to keep in mind is that because we've suspended the magnetometer underneath the multi-rotor UAV, we will get some sort of swinging effect due to the magnetometer being a pendulum back and forth. And what this occurs at, it's more or less a function of the length as well as some other factors that are input in, such as flight speed and wind and things like that. But you can see that it's a relatively low frequency signal, which you can see right here in the frequency domain by this blip and throughout the survey as we go along. And this highlighted section here is showing just the 2 nanotesla roughly amplitude of this signal. And this is, of course, compared to the actual target geologic signals, which are lower frequency in this case, which you can see right here with 400 nanotesla being the amplitude of this. And this specific target was a mafic dike that was flown over. So this is in contrast to when we look at the spectrogram of if the magnetometer is hard mounted directly onto the multi-rotor UAV. So the first thing we can see is that we've drastically increased the amplitude of the mechanical rotation, or this electromagnetic interference signal that's due to the rotation of the rotor, which you can see here. But the other thing that we can see is that we don't have our swinging signal right here because we've hard mounted it. So that's kind of a plus. However, the biggest issue that we find is that we have to keep in mind what's going on with these higher frequency signals that I was talking about earlier in the second part of this presentation, where we have very high frequency electromagnetic interference signals that are above even the Nyquist frequency of this 1000 hertz magnetometer. What typically happens when you have this occurring is that these signals will become aliased. And in this case, if you hard mount the magnetometer, signals are aliased, they're high amplitude, and they tend to bleed out as white Gaussian noise throughout the rest of the frequency components, effectively raising your noise floor, which is what you see here, where we have just this white noise basically throughout all the frequency bands of the system, as well as into your kind of target signals for magnetic surveys. So a way to mitigate this is definitely to look up and determine what your step back distance is for the specific configuration, and then look at ways to be able to filter out these high frequency EM signals if you're using the mag arrow, as well as the swinging signals. Or if you're using something like a GEM Systems GSMP35U, which uses a slightly slower sampling frequency, where it's actually not able to resolve these mechanical rotation frequencies, then you're just looking at removing some of these swinging signals. So a quick example just to run through, because I know I'm going to be close on time here, is looking at just removing these different signals. So the mechanical rotation, the swinging frequency, and what this kind of looks like highlighted in the time domain comparison, which I'll zoom into here. So what we can see is that our mechanical rotation frequency is a very, very high frequency, low amplitude signal here. And if we go ahead and low pass it, this is what the result would be, is just a smoothed out version of this, keeping still the swinging frequency, which we can see. Whereas if you go ahead and use this technique of low pass filtering, you can then again, as long as these two signals do not overlap each other, the swinging frequency as well as your geologic signal or your target signal, if it's for other different anomalies, then you can remove this as well and still keep your target geologic signals. So this is kind of what an end product could look like for removing these swinging frequency signals, which you can see kind of as blue overlapped on top of the signals that have been removed in green, which is just highlighting your geologic signals. So kind of as a wrap up to these mitigation techniques and conclusions for how to go about doing this, the first thing is definitely to look at what your offset distance is going to be. What this results in is very low amplitude EM signals, which is a plus. But the thing you want to keep in mind here is what these swinging frequencies are going to be. So in this case, if our target frequencies are somewhat lower than this, you can still put in a low pass filter to be able to remove these from the system. One thing that you can look at doing is slightly increasing decreasing the distance between your magnetometer and the UAV, which will increase your EM signal amplitude. But the other thing it'll do is increase your swinging frequency, basically putting a little bit more space between these two different bandwidths. Now, where we run into issues with hard mounting the mag is that you get these extremely high amplitude EM signals and the white Gaussian noise that comes across all the different frequencies within your signals, which effectively raises your noise floor. So for a lot of these higher end applications, this sort of configuration is not going to be something that is viable. And then at the far end of the spectrum, what we have is suspending it even further. And the issue you run into here is, yes, you're going to have very low EM signal contribution, but you're going to have also very low frequency swinging of the magnetometer that can overlap with even your geologic signals. So this is where you would need to include an IMU and a phase-based filtering for the different signals to be able to tease out which ones are due to swinging and which ones are actually due to geologic signals. So in conclusion, one of the first things when developing these systems you need to be able to do is have a good idea of what your sensor offset distance is. And this is kind of defined as the distance at which a geophysical sensor loses sensitivity to the drone's electromagnetic interference. This is going to be unique for each sensor's sensitivity parameter. So if I use a flux gate of 10 nanotesla sensitivity versus a 10 picotesla optically pumped magnetometer, these offset distances are going to be very different, as well as if I use a larger or smaller drone. The second thing that I would suggest is looking at your application and where kind of these discrete frequencies occur throughout these equations. So looking at specifically what kind of frequency targets you need to look at in the data you want to acquire, and then where these electromagnetic interference signals could potentially be overlapping with them through looking at these equations. And then finally, we want to be able to remove any of the remnant interference signals, even when we suspend the magnetometer. And these typically are the mechanical rotation frequency as well as the magnetometer swinging frequency. So as a final kind of figure, just to wrap everything together, I threw this together over the last couple of days, just with everyone presenting and looking at all these different techniques and how the electromagnetic interference characterization that I've kind of done with my research can play into all of the different techniques we've looked at. So if we're looking at frequency kind of plot here where we have gigahertz on this side and it's kind of these lower frequencies on this side, we can plot up, you know, for magnetic surveys, a lot of the geologic targets we want to look at are in these lower frequency bandwidths compared to where I've demonstrated the swinging frequency is, and these electromagnetic interference signals. This gets a little bit different when we're looking at UXOs for magnetometry, because obviously these are a little higher frequency signals within the data that we are looking at. So these have a large potential to overlap with the swinging signals. And then if we look at some of the other applications for drone geophysics, if we look at VLF, the frequency bandwidths for this typically overlap with some of the potential signals for the electromagnetic interference. So this will be something that needs to be considered. And looking at EM, obviously there's going to be a lot of consideration that has to be put into this just due to the bandwidth overlap of these electromagnetic interference signals and some of the very specific frequencies that are used for both frequency domain, time domain, and SAM methods, as well as others. And then kind of leading into some of the questions I was asking about the GPR section on the first day, we can see that most of the GPR explicit frequencies are up in the megahertz to gigahertz range that don't necessarily overlap with the electromagnetic interference signals that are generated by the multi-rotor UAVs. And this might be some of the reasons why there wasn't some of these noise issues that we were seeing when we discussed this in the first day. So I think this is just kind of a nice, interesting figure to open up discussions here towards the end of the day. So with that, I have lots of acknowledgements. I'd like to thank Ron, Morgan, and Lori for everything they've done putting this together. I think this has just been an absolutely wonderful day, and I really look forward to the discussions towards the end. So lots of the funding partners through scholarships for my research, particularly the SEG. I can't thank them enough for all the support they've given me throughout the years. And I'd be happy to have any questions that like to come up. Thank you very much.
Thank you, Callum. We are over time, so I'm going to have you answer your questions in the Q&A. I know you have a couple of them there, so if you would not mind taking your questions there, that would be lovely. Lori is going to start migrating everyone over so we can begin our discussion portion. Ron, would you like to say anything about that?
Well, I think some of what Calum presented at the very end there is really a good starting point in terms of discussing EM. And discussing the gamma ray talks, there seems to be a lot of interest in that, judging from the Q&A questions that have come up, and I think we need to touch on that a little bit. So I'm hoping the presenters, our panel discussion group, will be able to field some of those questions they've been receiving during our discussion session. And also, I've got to compliment every speaker here, outside of me, of course, that they've done an excellent job of presenting today, and really thought-provoking presentations. I think this is, in my mind, is at least it's starting to really move to the next phase of using drones. That is, doing things like gamma ray, EM, and I don't see it ever stopping. I think we're learning a lot, and these tools are actually beginning to really sort of expand and mature, and a lot to do though. So have you migrated everyone over there, Lori?
She's working on it. Callum, could you stop sharing your screen, please?
Yes.
Thank you. If anyone would like to ask questions, please unmute yourself and also turn on your video. It makes it a lot more obvious that you would like to speak. But we'd like to open the floor to any questions or comments, things that you'd like to be addressed by multiple presenters. And I'd like to add that we have plenty of subject matter experts who did not present in this who are present. So please feel free to contribute to the discussion, even if you are not a presenter. I know that we have had quite a few adding to our discussion in the Q&A, which has been wonderful. So I had a question, since no one else wants to speak first. Stephen, with your method, is that something that has, you'll have to forgive me because I know very little about that method, but is that something that sees a lot of noise from the drone? And also earlier this week, we were discussing the idea of combining multiple sensors on the same drone system. If it's like, it looks like you were able to mount it extremely close to the drone. So I wonder if you could partner that with one of the sensors that needs to be held farther away.
Well, yeah, that's a very good question. In fact, someone in the questions panel or in the chat also asked me a similar question. And the fact is that the gamma ray spectrometer is not influenced at all by the orientation of the drone, of the motors or anything. The only thing that its signal is influenced by is the measurement height, and also external parameters such as radon that can influence, but none of the way you mount it will influence the measurement. So this means that also the orientation of the sensor does not matter at all. In fact, I often get this point when we do measurements and we are in the process of mounting a gamma ray spectrometer. I get the question, oh, how do I need to mount it? Do I have to make any precautions? Do I have to stabilize it? Well, none of that has to be done because it's a passive system and it just measures the gamma rays coming in. The only downside of combining this with other methods is that the gamma ray spectrometer works based on its volume and mass. So ideally, you want to maximize the volume and mass of the spectrometer while keeping an acceptable flight time. So if you want to combine sensors, this will obviously add weight to it, which you cannot use for the spectrometer. So that might be an issue. But otherwise, you can easily combine it with the other sensors.
Oh, thank you. And I see we've got a couple hands up. Mohammed Hashedari, would you like to unmute and speak?
Hello, thank you for excellent speech. First, I want to ask a question from Steven. He says that that was my question. He said that when the orientation of this his probe is changing, then it does not affect the data at all. Of course, I'm not affiliated with this concept completely, but as far as I know, in well logging, when we have a gamma ray probe in a well and it's a standoff, I mean the distance between the probe and the well is changing. Or for example, the well is not exactly vertical and we have some angles between the probe and the wall of the well, then the results and what we get as data is changing, and this is a matter of that we must correct it. How he says that when the orientation of the drone is changing, we do not expect any changes in the data we get?
Okay, well, a very good question again. I must say that I'm myself not too familiar with well logging. I have some experience, but I can imagine that the situation is a bit different because small changes inside the well may be of a bigger effect, especially when the well is also filled with another material such as water, which will attenuate the gamma rays a lot. The thing is with drones, when you measure in the air, the amount of attenuation through a solid medium or a liquid medium such as water in the ground is many times higher. It's at least 3 orders of magnitude higher than the attenuation by the air. So when you measure with a drone, the height is important because the air attenuates the gamma rays traveling through the height. But so far we have seen that height differences of 1 meter do not influence the signal too much, especially if you take into account that there's an uncertainty in your statistics anyway, in your geophysical measurements for a typical gamma ray survey. So these height measurements, plus and minus 1 meter, do not influence it that much. And for big height differences, you can correct for that. So that's in the vertical or the Z direction. in X and Y and turning, it doesn't really matter because as said in the previous question, the gamma ray experiment detector is a passive detector. So it just records what's coming in. And the flux, the amount of gamma rays per square centimeters are roughly equal above a measurement plane. So yeah, it's not too much of an influence for drone measurement, but now I think about it, I can imagine that in well logging, especially when it's filled, it might be a bigger influence.
Okay.
Thank you. I think we have another question from Jeff Garney.
Yes, hello. First, I'd like to thank all the organizers and the speakers for just an awesome presentation here. It's been extremely enlightening. I do have a question for Callum, and that was when you're talking about the swing noise with the magnetometer system, is that related to the change in orientation of the sensor, as in it's a heading type correction, or is that more of a change in its place of the sensor placement with respect to the drone, as in you're still seeing some residual drone influence on that?
Very good question. Yeah, and it's a little bit of both and depends on where you suspend the sensor and what sensor you're using. So kind of to break this down, what I was showing there was actually the magnetometer swinging through the geomagnetic gradient throughout the survey as it goes along. And there's also with that a little bit of heading error associated to it as you get yawing back and forth on these pitches and more so rolling. I've done, so that's with the mag arrow. I've also worked with the, what is it called? The GSMP35U, and had that within the field of the UAV. And if you place that magnetometer within the field of the UAV and it's swinging, you get a substantially higher swinging frequency or swinging amplitude due to that. So even if though you place it outside the field of it, you still get this kind of signal due to it swinging through the geomagnetic field. So there's a little bit of everything. Good question.
Looks like Mohammed would like to ask another question.
Yes, please. I have a question from Colin. When we talk about the interference, it is not only due to those permanent magnets, oscillations and twitching of the drone, especially when the roll and pitch and yaw is changing. Of course, it has some kind of vibrations, and it is another source of interference. I think it is not possible to do some very simple experiments as he did, and we only change the vertical position of the drone or horizontal position, or even we make a circular movement to see all the possible interferences that can be done and can be made by the drone. Another thing is the source of this noises is not only the permanent magnet. For example, we have the coils, they can have some mutual effect with our transmitters. And of course, we may have some secondary magnetic fields produced inside these coils. And all of these effects can be considered. How do you consider all of these possible sources of noise?
Yes, you're very correct. What I showed was just the permanent and kind of induced components of this. There's also the electromagnetic components, which I didn't touch on, because if I was going to go through everything, it would probably be about an hour of a talk. So I kind of condensed this talk just to focus on some of the bits that hopefully can be applied, but you're completely correct that there's also at least 2 or 3 other signals that I haven't even touched on there that are also synchronous to these motors. The interesting thing that we found, and kind of one of the main conclusions, is that these are discrete signals, however, and they are synchronous, as the name suggests, with the motor to the rotation of the motor and the duty cycle of it. So, I mean, there's a lot of work that still needs to be done with this, but this is just trying to, you know, present a bite-sized piece that hopefully some people can appreciate.
Okay.
that it's low
Have
frequency
you
and stuff.
to drive those formulas for FIMF and FMR that you showed? All of these formulas are derived by yourself, or you have some sources or references for them?
They were derived by myself, and I am currently trying to verify them with people who actually make these motors and looking at the signals with it. It's interesting because you have to, one of the formulas I have there has a geometric correction in it because you have to consider all the different rotating fields and inducing fields and the directions of them. So it becomes quite complex when looking at very specific applications of it. And this is where kind of some of these formulas we developed may come in, and they may have already been developed elsewhere too. And that's what we're going to look at.
I really appreciate if you publish these formulas in some papers, if you mention to those papers so we can see them.
Yes, yeah, I'm currently in the in the works of publishing them right now and explaining everything. We ran through, as I said, finite element analysis, trying to explain this formula because it wasn't what we expected it was going to be. We were expecting one other thing, and it actually took me quite a while to try and explain this. So yeah, it'll be published, hopefully.
Awesome. I see that Kian has a question.
Thanks, Morgan. Yeah, I had a question actually that came up for me listening over all 3 days. I really appreciated all the presentations and the discussion. And one of the common themes that we just were touching on and have come up each day is the common need to better characterize the sensor orientation and motion. And this is, folks have talked about how this is a traditional issue in airborne geophysics that is, dealt with regularly. But most of the companies that, at least that I'm dealing with, who are working on developing geophysical sensors for drones are coming from ground surveys where that may not be as significant a consideration. So I guess I'm really curious, how do we achieve is there a need for better knowledge transfer between the traditional airborne geophysics community and the drone airborne geophysics community? And if so, how do we do that? I know, here it seems like most folks are drones. When we did the SCG AGU airborne geophysics, we had a mix of traditional airborne and drone folks, and they seem to stay very separate. So I'm wondering, is there a need for more synergy, and if so, how do we do that?
Yeah, I sent through, I had a discussion after yesterday's session with Ron and Raina about this whole issue of quality control and bringing everybody in the industry from, small operators that are starting out with drones right through to people with the sophistication of Brendan and Raina in terms of processing data to an airborne data standard. I mean, even as Brendan has illustrated, about half of the drone contract operators in Australia are flying data which has got still got problems and presenting that to clients. So there's obviously a great need to bring everybody up to scratch, avoid the problem of bad operators. There's nothing worse for geophysics than to have bad geophysics. And if there's a lot of people out there with the knowledge of how to improve the processing of data, for people that are actually moved from being ground surveyors and haven't actually worked in the airborne industry, that might want to do their own surveys, or they might want to employ a contractor. So there's a big need for standards, and there's a big need, I think, for a how-to manual. I just put that there as a comment. Yeah.
Let me kind of add on what Jeff just said, and that true that most of us that are starting to use drones and those that will be using drones in the future are coming from a non-airborne geophysics background. And so to be honest, I really was happy to see that Rainer and Brandon wanted to step in and talk about the problems that are occurring with drone mag data. But it's just not drone mag data, it's every geophysical data type. We probably do need to have at least some guidelines, if not standards. And I do think it's, as Jeff points out, it's kind of a cross association need, and I encourage the conversation to continue forward on us coming up in our own way as a group to say, these are the best practices or the guidelines to the best practices. And then maybe in some cases actually publish a formal standard.
I'd like to add that I would be really curious to hear Brendan's take on all of this, since he specifically kind of started that conversation for us today. And it would be nice to hear his thoughts.
Hi guys. Yeah, so from what we're seeing, there's definitely room for improvement in terms of just how data is being delivered to the clients. And I think given that most people don't have that background in terms of understanding how these data sets are being delivered in the commercial sense for airborne or heli systems, it's sort of a work in progress. And if they're not being given the feedback on how data should be delivered, well, then they're not really able to work towards it. So it's good to just sort of prompt that that conversation to be happening, which is what I was trying to get across, was that pointing out the differences between what we're expecting to see versus what we're currently getting. And there's quite a big gap. So definitely room for this to be discussed. And I think that should be the way forward.
Awesome. Well, it's nice to see such a large community supporting this.
Could I say something?
Absolutely.
In my opinion, a larger part of the drone community doesn't see what happened in the past. You know, we do fly a normal airborne geophysical surveys, and the drone survey is a normal airborne geophysical survey. So basically, why do we not take the decades-old knowledge from this traditional airborne geophysical community and just apply it to drones?
It's Rob Shives. Can I have a little comment, please?
Sure.
Absolutely.
I admit to being a neophyte when it comes to the drone world, and I find it really humorous, or maybe ironic, or I'm not sure what the word is. I come from a background of the Airborne Geophysics Group at the Geological Survey of Canada in Ottawa, and in particular with the radiation survey, so the radiometric gamma ray boys. And what's interesting is that when the drones started to evolve a decade ago or more, we in the airborne geophysics world, I think we're poo-pooing the idea that a little tiny thing like that could possibly approach the accuracy and the quality of an airborne survey. Isn't it interesting now that we're seeing that the drone world is not a passing fad? It's quite the opposite. They've offered all sorts of alternative platforms to situations where a conventional survey is less practical, let's say. And I think it is time. This was the one impression I had from the last 2 days plus today, is that there seems to be a disconnect that we've all recognized now between the established airborne geophysical decades of learning and perhaps what's happening from the ground up, if I could say it that way. And yes, I think this is an excellent idea that Jeff brought up, the idea of linking those two groups. We're already kind of integrated because there are people on this workshop that have a lot of airborne experience. And I think it's definitely crying out for not reinventing wheels, but adopting current practice, and especially in the QA/QC part, to really bring the drone surveying geophysics, be it gamma ray, which is my forte, or the magnetics or EM or other methods, up to the same sort of standards within the limitations of the platforms themselves. So this conference has been a tremendous eye-opener again for me, and I appreciate the organizing and the content. I think it's been very good.
Okay, thank you. One of the common problems I have seen in these days about the processing, some kind of the general questions. Today, Brandon's talk about it mostly, that when we macro leveling, we are always afraid that if we miss some of the geologic features, and always have this problem when we do the processing, and all processing methods have some their advantages and their disadvantages. I want to ask you, if somebody tries to use perhaps some kind of equivalent source inversion or common potential source inversion, and then try to reproduce the data instead of just a simple processing. I think if we try to use equivalent source, especially in magnetic data, we could see some better results, and we can say that all the problems we said about the levelings, we can solve it in this way.
Mohammed? Oh, can you hear me?
Yes, I can.
The most advanced person I know of is Gary Barnes, now Bridgeport. He was ArcX before, and he developed his equivalent source processing or technique, and it works like a bomb, both for FDG data and mag data. So if you really want to know, name is Gary Barnes. He had a couple of publications, and he works for Bridgeport, Austin Bridgeport now.
Good. So we can say that we can use it instead of those techniques that all of them were somehow problematic.
For really complicated surveys, like we flew FDG, that's full tensor gradiometry, gravity gradiometry, in the Rift Valley, which is in East African Rift Valley, which is an extremely difficult area to fly. And what I can say is that that product of his is really good.
Awesome. I think Brendan wanted
So
to...
you can say, excuse me. So you can say if we don't use it on drone-based measuring data, it is only because it is very costly and it is not feasible to use this technique. That's all.
It's not really the standard method to be used, but that specific group actually did develop it into a practical, usable stage. And but as far as I know, that group is the only one at the moment that provides that technology on a commercial basis.
Thank you.
So Mohammed, I'd like to add, so I think what you were trying to say was, why don't we do sort of more inversions compared to just the data processing that I was mentioning? Is that correct?
Yeah. Yes, exactly.
Yeah, so my take on this is that inversions tend to blob the data. So you're kind of looking at very different data sets. Inversions are typically better for modeling sort of discrete targets, and the processing that I was talking about, the micro leveling and timeline leveling, those kind of things are more for the gridded data. And you should typically use these two data sets as a side-by-side thing and not choose to do one over the other, as they'll be highlighting different things. Doing gridded, like processing of the gridded data and subsequent derivatives and interpretation of the data will highlight more structural information, whereas modeling using inversion methods will be able to sort of delineate your discrete targets a lot better, but you might not get these structural information that the gridded data will have. So you kind of got to use them as on a side-by-side thing rather than one or the other.
Brendan, I don't think that this was my question actually. When we talk about the equivalent source inversion, we just try to make some hypothetical source is located on the Earth's surface, then can produce our data. We actually use the non-uniqueness of the source of magnetic data to produce some hypothetical source, and then from this source we can reproduce all of our data. It is another thing that if we try to use our traditional and common inversion techniques to find the structures and the models underground, this is something else, I think.
Okay, yeah, then sorry, I misunderstood your question then. I'm not too familiar with the equivalent source method, so I'd probably have to look into it and maybe contact you outside of this talk, if you'd be up for that.
No problem.
Over the past few days, since we've had more than 100 people attend this workshop, which I got to tell you that for Morgan and Lori and myself, that's very gratifying that you all joined us and contributed to our first effort at this, and I thank you for that. I think one of the things, though, that I found besides the talks, which were all thought-provoking for me, that I found to be most interesting was this discussion group. They asking the questions. We all come from various backgrounds. We've all recognized, and I'm going to kind of be a little contrary to Rainer's comment that drones are all about airborne geophysics, and at least the geophysics side of it. Drones offer a unique airborne geophysical platform, and we're not at the end of actually beginning to explore that. In fact, we're at the beginning of exploring how to use these platforms, how to correct for the data, how best to fly the data. And what Jeff brought up in terms of establishing some guidelines or some standards, I think is very, very apropos to our furthering the mission of using drones, helping people who are not coming from an airborne background understand what the airborne guys have learned over the years, guys and gals have learned over the years, but also helping those of us who are actually working at developing unique solutions to help understand what we should be doing. And then I work a lot with people that are getting into drones that are service providers. They're actually getting into drone geophysics who are service providers. They're flying drones for other missions. And what I see is that they just don't have the understanding of the geophysical technology or the processing or the inversion or any of that. They're basically, it's all a pretty steep learning curve for them. And so if what we need is to help guide them. So I think what we need at least is to help guide them so they're not making big mistakes and selling projects where they're actually delivering pretty poor data. We want to avoid that. And so I think the best way to avoid that is just to educate and inform. And what Jeff is proposing is part of the process. And so I'm sort of in my own way reaching out to you all to say, hey, if you have something to contribute, you feel strongly about this, or maybe not so strongly, but you see that it's an important thing that we should be doing as a community, then let's get together and chat about it and talk about how to move it forward, so that I think it'll be a benefit to the entire community. Myself, whether you're using drones or not. So I don't know what is our time. We're into our sort of our summary for the workshop, and I wanted to point out that over the course of the last 3 days, we have listened to speakers on opinions about the geophysical roadmap, where we're going with drones and what the geophysical sensors will be. We've seen some of those that are emerging right now, where we've addressed some of the processing issues and the visualization issues. We've not particularly addressed the inversion issues. I think there's or the interpretation issues. I think that's actually in the future discussions, because right now what I see is that we're really trying to sort out how to get good data. We've addressed had several speakers on GPR, which I find to be very interesting. Most of the mineral exploration guys aren't using GPR, but there's clearly some issues that where drones are, or problems where drones are going to be applied in doing good GPR data acquisition. I'm really happy that we had the GPR as part of our program. We actually, I should say, we had a seismic speaker who had to drop out. But I see in the future maybe for more near surface, but maybe for more sort of resource exploration problems, we'll start seeing more seismic talks in future summits. We had a whole bunch of discussions on magnetics. That was our entire day yesterday. And what I was actually quite gratified to see is that we are not only discussing scalar magnetics, the type that gets commonly used, but we're also seeing people that are using vector magnetometers in very unique and innovative ways. And what I anticipate is in the future, we're going to start talking about what to do with the vector mag data, although everything that I've seen from a vector mag has really been boiled down to a scalar measurement. And then we're seeing the issues of sort of the problems with magnetic data that are coming to fore because of a lack of experience in how to deal with drone mag data or how to deal with airborne mag data by the operators. And then I was real gratified to see and happy that we had a gamma ray spec talk. I think that's going to be a subject for great discussion and great presentation in the future. And then I want to thank all of those, Calum, Brandon, Rainer, everybody that really kind of honed in a little bit on the QC/QA and the data processing issues. Those are big things in my mind that we're not done talking about. We're going to end up, I hope we end up developing, kind of bringing it around to what Jeff was proposing, that we'll develop a set of guidelines, if not standards. I'm always opposed to standards. Well, not opposed, but I find standards in the engineering world become a little bit of a constraint. And in the geophysics world, we're always in the process of inventing and reinventing. So, and standards can be a constraint to our ability to do our work. So I want to thank everybody. I'm sort of for Morgan and Lori and myself, for participating, for being a part of this first summit on drone geophysics. And we're making the pitch to everyone here that hey, if you want to pitch in and help us kind of make the next one happen, we're open to it. We need this was a fair amount of work, but and the next one we hope will be will release us from some of the work we had to do on this one, but hopefully bring in new voices. One of the fundamental principles that we were operating on, it was getting as many voices from people that are doing things in the world of drone geophysics as we could. And we are actually quite pleased that we got all of the presenters that we got. We know that it's if you've ever been involved with a conference, you know the first one's always the hard one to get off the ground. Hopefully we've launched this, and that next year you will all want to contribute. If you will all want to attend, and hopefully most of you will be vying for a position to contribute. In that and I'm kind of at the end of my sort of summary and closing remarks. We're getting close to the networking, the end of the conference, which is, or the end of the event, which is in about 80 minutes. And then we have an open call for a networking section. We plan to leave open for people that have, want to continue to discuss things on various topics, whatever is important to you all. Morgan, do you have a few things you want to say?
I do. I wanted to say once again that we really, really appreciate our sponsors' participation in this, and that this was largely possible because of the near-surface SEG community. I wanted everyone who participated to be aware that we have a quarterly newsletter, and we would love to see content. So if people would like to talk more about what they're doing and reach out to a larger community that maybe isn't in this niche specifically, that's a great place to do that. And then also, if there's enough interest, we would be willing to discuss the idea of a special section of the leading edge. So if there's interest in that, please reach out to Lori. She'll make sure that we all know what's going on and the right people are involved. And then on that same note, I did notice that we had a couple people who seemed to want to contribute a little bit. So as we move into this next networking session, I know some people will move on, but For those who want to continue the discussion, we have about an hour left where you can continue that. So Dennis Woods and Lee Fox, if you would like to share, please feel free to use that time to speak your piece and ask your questions. I'm hoping some of our presenters will stick around and continue the discussion. And then the other part that I'd like to add is we're going to share a post-event survey with everyone. And the primary purpose of this is to get a feel for what parts of this event were really valuable and make sure that when we create the next event, it really meets the best needs of the community. So if you can take the time to fill that out, we would be really grateful. And last but not least, this will all be available via video, but it's going to be a couple weeks. So if you haven't gotten it before the end of the year, I would reach out. But Lori has a lot going on and she has some work to do before this can be released. So thank you to everyone for your participation. This has been wonderful.
Hi, everybody. Just following along with what Jeff and what Ron were just talking about, some sort of standardization for drone geophysical surveying and contractors specifically. One thing that hasn't been touched on is safety. And there is, most of you probably are aware that there is an International Airborne Geophysical Safety Association, IAGSA, and they are considering the impact of drones from a safety point of view. Of course, it's not quite the same as manned aircraft and that sort of seriousness, but accidents happen. And the best way to learn from accidents is to document every single incident that has ever happens. And the way to do that internationally is to belong to IAGSA and submit reports and be part of the international team to monitor and hopefully make using drones and all airborne geophysics a safer enterprise.
Dennis, I applaud you for bringing that up. I didn't quite get your question the other day when you asked, well, how do you avoid falling crashes? And my answer is that most of us that fly drones is that, well, you really can't you can't stop crashes. You just try not to have them, and you do that by field procedures. But I see where you're coming from now in terms of developing sort of practices or standards or guidelines for people using drones. I don't think that that was on top of my list as the important things. I think I'm more concerned about data quality, but I do see it as the drone industry starts, drone geophysics industry starts to expand, and we get to we're using bigger drones, we're having more risk involved with using the drones. Then yeah, we need to have that, and now's the time to start. Now's the time to have the discussion. So,
I completely agree with Dennis. It's a very good idea. I actually had it in my talk, but it had it made too long, because IAGSA did a lot of good for the airborne industry, and usually a contract or any specifications require that the contractor is part of IAGSA. And I think there could be a good lobbyist for droneologists, because let's face it, the biggest obstacle to the growth of the drone industry is legislation.
It is one of the, I agree that that regulations are going to be one of the things we're going to have to battle as the years come. Leo, do you want to turn on your mic and say something?
Mute. Well, I'm really just an observer here. We don't use drones, and we thought about it quite a bit, but we haven't figured out how to use drones for magnetotellurics. So I'm tuning in here just to find out what the state of the art is. We also make controlled source systems, transmitters. So I think the example somebody showed in Germany, where they were using grounded dipole, the receiver was drone mounted. We do have clients doing that already. We supply the transmitters and they supply everything else. So I guess we're in the market at one remove. So let's hope it all takes off.
Awesome. Sean, I see you have your hand up.
Yeah, hi there, everybody. I find it interesting that the question of safety came right before the comment on legislation. There's, as a new operator, I've found that getting the survey plan together in making these submissions for getting your permits to fly an area, especially depending on some of the more restricted airspaces, you've got to have pretty much everything laid out. However, on the safety side of things, the only crash I've had so far in the field has been where the topography intersected the flight plan because I didn't have a clear idea of the survey extent. What I'd like to see moving forward is a way to make the flight plan on the fly in the field, so we can take into things like consideration of the topography and how it changes, as well as obstacles that are flying the way. And then on the other side of things, with the permitting, just having a little more flexibility in the survey planning stages. Just I want to be able to do things on the fly in the field and have a tablet in my hand saying, all right, this is the area, this is what I'm looking for, and being able to interact with the drone more. When I pre-plan a flight, these flight lines that are set up ahead of time, a lot of the software that's available, like from Pix4D and from UCGS, these software packages, they don't make it really simple to take over as an operator. I've had issues with Pix4D and the mapper where I'll send it off to start the survey. I'll see a tree coming up and I'm like, okay, I need to take manual control over this flight, and the response of the drone isn't immediate, or they try to override each other. There isn't a lot of communication there. I guess where I'm going with this is just I'd like to see better user interface and be able to do things on the fly a little more.
I'm sure
Yeah, I
that-
might have a comment for this because you are talking about legislation, but things like planning the survey path in the field. Well, I'm from the Netherlands. I think the regulations allow it because the operators that we use do this in the field. I think a bigger problem is that the legislation everywhere is different. I know we did some work in Germany, and I know in Germany, each district has its own set of rules, set of guidelines. So it makes it very difficult if you are an operator from one place to fly in another place. So I would say make it more a global, to have the same regulations everywhere. I know at least in Europe, they are trying to smooth this out, that everywhere in all European countries, you have the same legislation. So if you are a drone operator in one country, you are allowed to fly in the other countries. But I'm not sure what the current status of this is, but well, that's a comment from my side.
My flights are in Canada currently.
May I comment this? We MGT did a lot of flights out of Europe. In Europe, we never had problems to get flight permission, even if the regulations differ from one country to another one. The most difficult country is Austria, but all other countries we never had problems. I also have experience in Turkey and also in China. I was 5 times in China. and did surveys there. Of course, all time with a contact with a company in China. We are now in Norway, and we experience that the regulations are different to Germany, but it took us 1 week to get the permission to fly. But most important was we had to get a pilot license, which was not easy because everything was in Norwegian language. And we had, thanks to Google Translate, we were able to translate it and prepare ourselves to receive this, to achieve this pilot license. It was quite costly. It costs almost 800 euros, but we now are allowed to fly everywhere without notice in advance. So this is my experience.
Kian, you have your hand raised. Would you like to speak?
Yeah, I wanted to just comment on Sean's question and follow up, because it also really, to me, dovetailed with some of the other comments earlier about non-geophysics contractors getting into geophysics and considerations about training. What occurred to me was that, you know, there are tons of webinars out there and trainings on what software is available, what tools are available, but they're typically from vendors. So if you're actually trying to do a cross comparison about, you know, what kind of flight software there is, or that sort of thing, there's not a lot. And that might be when we're talking about roles for sort of joint near surface group collaboration, that might be an option to consider, is, you know, a webinar series over time to help people see sort of what are the tools that are available to us out there, but not just from a single vendor perspective, but something that's more neutral and can compare them across. Thanks.
Can I change the subject, or is there more follow-up questions?
You can change the subject. Go ahead.
Okay, it's a question to all the radiometric operators. Is anybody linked to CTBTO, you know, the Comprehensive Test Band Treaty Organization? Because if there's an event recorded from their global seismological and infrasound network, then they have the right to inspect that site. But they have to do it in a very short time. And if the incident should be real, there is a problem to access the area. I would like to go in there if there was a nuclear incident, but that is that would be the prime destination for any drone survey. Is there anybody with contacts to the CTBTO?
Well, as to speak of this gamma ray, I might answer this, but we don't have these contacts, and we have tried some of these things, and we also are in contact with the IAEA about this, but this is still mainly geophysical and not so much of monitoring nuclear accidents. And to be honest, I must say that I'm not sure if the field is the same. I mean, both are using radionuclide identification with drones, but in case of nuclear accidents, you have a whole different kind of survey because the concentrations are much higher than with the geological survey. So I think that the lessons learned from the geophysics can be applied there, but I don't think they are the same.
Well, that's a prime advantage of your gamma the processing software, that you just plug in the isotopes into the calibration files and off you go.
Yes, that's true. I mean, it is possible. If you can plug our sensor on a drone and just fly in this area, and this is also what I've been saying, that it's ideal for such cases. But unfortunately, nuclear accidents don't tend to happen too often, so we do not have that many case studies of this.
Okay, well, just a thought.
Yeah, well, I think it's a good suggestion, and well, what I can share, we try to get in touch with people that are involved in Chernobyl to map this area, and in fact they were not that responsive to do these kinds of measurements. I think the thought of flying around with a drone in these kinds of areas is not that well, they're not looking forward to this. But I must say, not with a man. No, with a drone. And later I saw a group from England who were able to do these kinds of measurements, but as said, they used much smaller detectors, so a different kind of survey.
Okay.
I've got a question for Stefan about your radiometric data. Do you actually do what they call deconvolution of your data so that you can come up with equivalent squares or geometric figures on the ground, which is the equivalent concentrations of the various three elements, and then comparing each of the elements compositions to soil samples and so forth. This deconvolution method is used in gamma ray geophysical logging and so forth. I think a guy called Peter Gunn, I think it might have been a Wiener transformation or something like that was used as well. Do you use that technique?
Yes, we do it. What is conventional from the airborne world is using a technique of full spectrum analysis or windows analysis, and what we do is full spectrum analysis, and there's a little bit of difference to it. The biggest difference is that for full spectrum analysis, you have to have some prior knowledge of the response of your detector. For this, you need a calibration procedure. But yes, we do it, and we also apply corrections to map the data collected at a certain height to the equivalent concentrations in the ground. Because this is indeed a very important thing with drones. If you move to a bigger height, your signal decreases, and in the end you are interested in ratios between the elements, but also in the absolute concentration. So yes, this is a big topic for us. In fact, this is one of the major topics of the PhD research that I'm doing, so that we can map these absolute radionuclide concentrations in the ground.
Yeah, thank you for that. I mean, just on that matter of research, just coming back to this committee idea, one of the advantages of a guidelines committee would be to identify areas for research for academics, and then hopefully that will generate the interest in getting research funds allocated. And if it carries the weight of all the community, then those recommendations, and there's a greater chance of research being focused where the community, the drone community wants to be focused. The sort of work that Callum's doing, for example, is a classic example of that detailed research that's going to be needed. I would think once we start trying to push the drone measurements to even greater sensitivities, for example, for sound measurements and so forth, the processing going to become that much more critical in terms of getting the levelings right and all that sort of thing. So there may well be research ideas that are generated by a guidelines committee or standards committee, depending on what you want to call it.
I want to change the subject completely. I was interested in to see some talks about using drones in the seismic measurements, and I think it was in the primary schedule. Is there any other chance, or perhaps other similar meetings about using drones in seismic? Because I think that it is the most innovative technology that has come, and it will change a lot all the measurements. But you know that the seismic measurements is very costly, and if we can use drones in seismic, then I can say this is a revolution, actually.
I don't know of anyone who's currently hosting seismic specific drone related events or talks, but I do know that Ron and I both hope to bring some of those companies working on seismic or groups working on drone based seismic into this event for the future. We we originally had one presentation discussing that, but they weren't able to attend in the end. So I would say, from my perspective, stay tuned for next year.
Talk to Lockheed Martin.
I'm sorry, can you repeat that?
Talk to Lockheed Martin.
I'm going to make a comment that if we get all the drone related talks into, I think we could potentially double the number of speakers that we had at this particular summit, and that actually brings up an issue for those of us who are trying to organize it. Is that how do we take something that we started out as initially a gathering event that morphed it into an online event, and we felt that at the time that it needed to be split into 3 days because you get a little bit tired after staring at your computer screen all day, for 8 hours. So it was really more to thinking about the presenters and those that are attending, giving them a break. But if we ended up doubling the number of talks, that just changes our dynamic totally as well. So if you have any thoughts or comments or suggestions about how to move forward with the next Summit on Drone Geophysics, or engaging in the Summit on Drone Geoscience, let us know and help us. I actually find that, as I said before, that these discussion groups are really important. Important for me is I get some insights into what you all are thinking. I kind of live in my own little isolated world of drone geoscience, and I really find it very interesting to find out what your perceptions are and how. And please don't hesitate. Let us know. Let Morgan and me know. Our emails are readily available. It is. We're into. When we set up our networking session, we thought this might be the time where those of us who are in the right time zone might pop open a beer or a bottle of wine and actually relax a little bit. I just don't see it happening in Australia at this point. And then actually for me, it's just about noon, just after noon here in Denver. But also, I guess what I'm leading up to is to say that if you have any ideas of how we can actually improve this, our presentations, we've had a really good 3 days. We really want to work to actually improve it and understand how to use the media. That I think all of us are trying to do that in this world these days, because we're doing a lot more sort of online type media stuff. Let us know and help us improve this. Well, anyway, I just wanted to make sure I got those thoughts out while I still had them. So.
I wanted to pose a question to the group, and it's not necessarily a one size fits all type answer, and it's not necessarily something we have to wrap up, but I'd like to start people thinking about it. So the question that we had is what would you like to see from this industry going forward? I think we've talked about it a little bit already in terms of maybe some new regulations and some discussions about safety, but beyond that, I'd love to hear some thoughts about types of software, types of equipment, services, methods, like where can we grow, and what kind of ideas do people have about the future of this industry that maybe we haven't already started to talk about? So I'll drop that in your lap and then just let it sit.
And there was something missing, and that's hyperspectral. It was initially announced that somebody would talk about it, because there's a guy in South Africa called Laurent D'Amelio. He gave at whatever 2 years or was it 4 years ago a couple of talks. The guy is somehow linked to French military, but he gave a couple of talks about hyperspectral, and not really the full hyperspectral thing, but he had a couple of sensors where you could tune your spectral bands, and you would go out with a PIMA or ground spectrometer and identify your absorption bands, and then you would fine tune your 2 or 3 or 4 little drone sensors, and it would fly. That his idea was go for precision farming, but that is one field that wasn't touched at all here.
Well, we specifically kept away from the remote sensing stuff for this summit. Rainer, it's something we see that needs to be addressed. It probably needs its own summit. But in 2 years, we're hoping to actually expand this to include to what we're calling currently is a summit on drone geosciences, which we really want to include the remote sensing technologies. As you would probably view them as geophysical, remote sensors don't quite have that position as yet. So, but thank you for bringing it up. We really wanted to have a forum for people that are working on these emerging technologies, the gamma ray, the EM systems, and then working on the technologies that have become somewhat standard, the magnetics, for example, that we felt that we didn't really need to muddy the water anymore. We have plenty of content, at least some topic content. I've got to say that when you start off putting on a conference like this, you start off with your fingers crossed, because you don't know if anybody will contribute. And you don't, so when you reach out and you start trying to get people to contribute, and they agree, you're thankful. You're thankful, because then that kind of helps you build the program. And then at the very last minute, this happens with all conferences. We had a few that had to drop out. And fortunately, we had a couple groups that speakers, one of them being Stephen, and that were willing to step in and actually contribute, bring something that was really, I think, a very important component to this particular summit. Anyway, I'll stop droning on.
No, much appreciated, and thumbs up to everybody, to all the entire organization committee. It was a nice very exciting 3 days.
Well,
I think.
Go ahead, Johannes.
Yeah, I think the problem is we cannot gather together and have a beer together. I think this is a big problem.
I think so. I'm hoping by next fall that this COVID thing will be much better handled than it is currently, or has been currently. Hopefully in the United States it will be, and that we will be able to put on instead of just a purely online sort of summit, we will have a partial gathering summit where that at least that's the vision that we're currently working with. I think there's a lot of benefit to this online stuff, but I do miss the fact that we can't sit across each other and have a little bit more comfortable chat. And I hope we can get back to that soon.
And,
one of the formats we've discussed for the next one is maybe trying to organize regional locations where people who are in similar places can meet to participate. So you'll get some component of the networking, since we really don't know what next year is going to look like yet. But what I would like to see is we still have this global cooperation and participation from speakers. I think it's very enriching. So maybe a hybrid where we have local gatherings and presentations are broadcast between those local gatherings might be more on the order of what we accomplish for next year.
Yeah, you know, we're trying to figure it out. And if you guys have a good idea, or it doesn't matter if it's good or not, if you have an idea how to help us make it happen, we'll certainly entertain it. We want this, and hopefully the future ones, this event and other events that I see could be spawned from this kind of event, to be really beneficial. You know, we might be focused on sort of, you know, this is a near surface sponsored thing, but a lot of the tech is really appropriate for essentially non-near surface problems. And we need to bring in my mind, we need to bring our customers into the conversation. So I'm hoping that'll happen soon.